that was the only time. That never happened after that. So yeah, so now he powers up and leaves everybody else in the dust. So it's a pleasure to be here. You know, we've been into Zurich Airport tons of times, but have never actually been to Zurich. So this is great. And I must admit, when we arrived here yesterday, it was the first sunny day that we had since we left. So we've been in the Netherlands, in Delft, and went to Bonn, and then we went to Vienna. It was cloudy, rainy, cool. So actually the opportunity, Lindsay was so excited she had sunglasses that she brought for the trip, and she hadn't had a chance to use them. So it was good. So this is the disc. Every year the SEG puts on or sends somebody around to various places with a topic that might be of interest. And this year they chose me, and they also chose to have something different. They usually have something on seismology, but this year going for electromagnetics fundamentals and applications. So in the traditional disc, whoever presents this usually makes a big book and provides that. We don't do that this year. All of our resources are going to be on the web. They're going to be live, and I think that will ultimately help. But I'm not sure if people have had an opportunity to download the the slides or not, but they are all available. Before I start, I wouldn't mind actually finding out who the audience is, what your background is, or not necessarily your background, but what you're doing, and in particular, what, if any, there are as far as connections with the EM. And the reason for doing that, first of all, we want to know what you're doing. But secondly, is that we have a number of case histories that we can show during the course of the day. And kind of depending upon what interest there is, then we'll go one way or the other. So maybe I'll start at the back.
Morning. Yeah, my name is Joseph. I'm a senior scientist in the UG group. I had lots of interactions, actually, mostly with ERP. Worked with it for my PhD, with the EM methods. Otherwise, I haven't used them myself very much. But, okay.
I'm Sergej Schnetzbach. I'm a senior scientist also in the EEG group. I'm mainly working with seismic methods, but I've been working a bit with geology.
So Agostini Lonti is my name. So I just joined the Swiss Seismological Service 2 months ago as a postdoc. And then I will be working on assessment of the tsunami or slope instability on the lake also. So, and then I've mainly used the passive seismic or ambient noise technique for subsurface very shallow characterization. And with the electromagnetic method, I have no proof, but from the email it was appearing that these methods could also be used for slope stability analysis. So that is why I think this course, I look forward to doing this course.
My name is David Xu. I'm a first year PhD student and my supervisor is Sudi. And I'm working on the seismic full waveform version. And previously I worked on the square reverse time equation in University of Alberta.
I saw you back. Were you working with Marisa? Yeah.
Hi, I'm Lisa. I'm Marisa, PhD students, and my background is more in glaciology and remote sensing, but specifically what I'm doing here is working with airborne GPR for estimating the thickness of the alpine glaciers.
Oh, okay.
I'm Luca. I'm working at the seismological service here, and I do forward modeling for induced seismicity. So I'm mainly involved with numerical modeling for nuclear waste repository at the moment. So my goal is, I'm interested because it may be interesting to monitor fluid flow to see what can be the capabilities and if it can be extended to work underground as well. To understand.
Good.
Yeah, I'm Jerry. I've just worked my master in geochemistry, so maybe I'm not really at the right place, but I'm just really curious about methods for investigation in the ground. So just checking that.
Theo, I'm also a PhD in the EEG group. I'm mainly working with seismics and acoustics in general, not so much with EM, but all of this knowledge still close by. I'll just take it and see what I can take from it.
Okay. My name is Peter Virginia. I'm also in the EEG group. Most of these people are mainly, mostly, pretty much only work with seismic. However, I'm teaching a course which I'm also teaching GPR, so I thought that the pressure would be good. And in general, I took the chance to just go to the refresher of my bachelor studies in EM and so on.
Okay, good.
I'm Sabina. I'm visiting my son in Zurich. But I'm actually a geoscience consultant working in Moscow. And we came along with a lot of EM things. I'm basically, my background is seismic reservoir characterization. But in exploration, you grab everything you can get hold of to improve your accountability. And I think I'll get a lot of background information today.
I hope so. Okay. So that's, yeah, I must admit this is a bit of a different audience than we've had before. So it sounds like a background in ERT, GPR are the two main strengths. Not a lot of people have done EM. Hopefully by today, and today might see a few things. Before I start, I'd really like to thank Hans Rudy. Wherever we go, I mean, you can. So we're giving this course in different places around the world. That is key in all of this is the local host, somebody who's actually on the ground and can get people out. And Hans Rudy's been extremely enthusiastic about having us come here, and has done work to get all of you guys out here. So I'm very pleased and really want to thank him. Perhaps before talk too much, I'll just give you some idea of what a bit of history and who I am, since I know about you. I was inspired by a couple of pioneers in electromagnetic inverse problem, and in the inverse problem in particular. Bob Parker was my supervisor, and there's two guys, George Backus and Freeman Gilbert, who were really, I think, the pioneers and the fathers of the geophysical inverse problem. To kind of set the scene about where we are, I think if you look at, this is a time scale here, if you look at about 1975 and ask, well, what kinds of questions could we solve? We could basically solve the 1D MT DC resistivity problem, 50 variables, something like that. By the time you 1985, the 2D DC resistivity in IP, sort of 1,000 variables. 1995, the 3D problem. So you can see the progression of 1D, 2D, 3D. At this point, gravity, magnetics, DCIP, so sort of 100,000 variables in that case. By the time we get to 2005, we can solve the full 3D electromagnetic problem, both in the frequency and the time domain, with a few sources. A major event came in here with direct solvers and multiprocessors that then allowed us to solve the 3D EM problem that actually had a lot of sources attached to it. And yeah, so all of this, you can sort of see the progression of the advances in the electromagnetic inverse problem with being advances in computing. So that's one big advance, that we can solve the inverse problem. The second is that we now have really unlimited amounts of just high quality and high quantity data. So we can, there's probably large-scale groundwater studies in California, offshore hydrocarbon de-risking, looking at EM and trying to decide whether you should spot the drill hole on what's potentially a hydrocarbon or just possibly salt. And then we've got large-scale surveys. Here's one for Australia. Each of these dots is a magnetotelluric station that they're covering the continent on. So we've got lots of data, high quality. We also have a lot of open source resources that are just kind of coming on stream now. The last 10 years has seen huge amounts of development of onshore open web resources. That allows us to collaborate, share, test changes, do some interactive computing. And my group at UBC has been very instrumental in developing something called SimPeg, which is simulation parameter estimation for geophysics. Most of the work that you're going to see today has been done through there. This is open source software. There's also other things too. There's a PyGimli and a few and many other things. But open source has been key. And applications, we have lots. Electromagnetics can be used for minerals, contaminants, water, geothermal, unexploded ordnance, hydrocarbons, slope stability, geotechnical problems. I guess a lot of problems are more involved in this, and maybe some aspect of this compared to others, or maybe a bit of geothermal. So it seems like we got the basic ingredients. We got application problems, high quality data. We've got the ability to invert EM data sets and web tools to communicate. So what's the roadblocks? Well, there are actually quite a few. In general, I think a lot of geoscientists just don't simply realize the role that EM can play in solving a problem. And then they don't understand the technique. The terminology is confusing, right? So people talk about in phase, or they talk about real and imaginary data. So, that's often kind of confusing, especially to seismologists. And the other thing is that EM is complicated and it's unintuitive. So unlike seismology, where you can see it, you put a wave in, get a reflection back, and you get some kind of a signal. Same is true with GPR. You actually look at your data, and you got a map of geology, some information about geology. Electromagnetics, you can't do that. So you have to unravel it completely with respect to inversion before you get anything. The other challenge is the question of, okay, what's the connection of my problem with the various physical properties that are involved with electromagnetics? So, is there a connection, and what is it? And then if you decide kind of on this, then there's a question about, okay, what types of surveys do I choose? Do I do a DC resistivity? Do I do something in frequency, in time? Where should my surveys be? On the ground, in the air, underground? And what do you expect for resolution? It's important to have an understanding of what you can expect, because otherwise you might have some false hopes. And I think this is sort of a comfort level too, and that is that, are there any situations that are similar to mine for which EM has been applied? So if you've got a problem and you've seen that somebody else has solved a similar problem, then you feel like, oh, maybe I got a good chance here. So what's the roadblock? Those are them. And what the goal of the disk here is really, I just, by the end of the day, kind of get rid of a lot of these roadblocks and let's just get rid of them. So we're going to kind of try to step through things today so that these things here, which perhaps were impediments, are no longer impediments by the end of the day. And I think we're in the ability to take advantage of a perfect storm. I talked about problems with high quality data, got the inversion capabilities, web tools to communicate. So we can put it all together, and that's really what the disk is for, is to try to join these things. And all that I think is a really good idea, but we're sort of missing one important ingredient. Anybody have a suggestion about what that might be? Important ingredient to make all this work? Elizabeth? People, exactly. We need people. So I got two of them as co-presenters. There's Lindsay, who's sitting here, depending which leg we're on. The other one is Soggy Kang. And then there's all the rest of you guys that are sitting out there that can actually make all this, this work. So the goals for the disk, want to show you, and really, I'd really like to inspire you actually, by the end of the day, so that you really might think of EM in your applications. And we're going to do that by, first of all, seeing a variety of potential applications and look at the effectiveness of them through case histories. We want to build a foundation, because the foundation is extremely important. If you don't understand some of the basics, then you're going to misapply the technique. So we'll look at the basics, and the group has worked very hard to develop a whole bunch of apps. These are application modules that run interactively on the web. These are all open source, and they're a way of actually learning material in a very, it's kind of a fun way and also a very insightful way. We have an open source resource that we're developing. It's EM GeoSci. Has anybody tried to sign on to that? Okay. Oh, one. Good. So that's where effectively our textbook lies. As I want to set realistic expectations. And the other thing that we are attempting to do, and I think we're actually making good progress in a lot of places, is really promote the development of an electromagnetic community. We've got open software and capturing case histories. And as we've been going around the world, getting more and more people kind of communicating together about EM problems. Here's a cover. It's a book. I noticed Hans Rudy has it in his office. How many people have actually looked at that, recognize this? This is a book that was published by the SEG. It's got a chapter in there by Ward and Homan that outline the basics of electromagnetics. It's a wonderful chapter. And it's kind of a Bible for most students who come through electromagnetics. And what we are attempting to do with our source EM GeoSci is that we're kind of capturing this and sort of making it live. So the front cover, when you enter our site, has a tendency to look like that. We'll talk more about that later. What we're seeing also here are something called the case histories. We have parsed our examples in case histories up into a number of different steps. In fact, we've had case histories that have been provided from here, from ETH. One on rock glaciers, which I will show you maybe later. Case histories have been parsed into like a 7-step framework, and I think most people who do applied problems would probably parse it up this way. First of all, you've got your setup. What's the problem that I'm interested in? What do I want to solve? What are my physical properties that are of interest? Which survey should I use? What data do I collect? What's the processing? What's the interpretation? And what's the synthesis? How do I actually impact on problem? That's a nice way of kind of parsing out everything, and the ability to do that really fosters communication, because when you're talking to somebody or interacting, kind of knowing where you are on this circle is really useful. So we'll be seeing a lot of case histories, and they're all kind of parsed out. It's all interactive, so the resource that we have can be edited by anybody. You can ask questions, you can see changes, and it's all licensed through Creative Commons. Why apps? Well, if I look at this equation here, I got Maxwell's equations, a couple of them, and they encompass a lot of things, but they don't really provide much insight. However, if you're able to convert that into an app so that you can change, change the frequencies or look at different fields or fluxes, then you can start to ask questions and then also get some insight. So how do we achieve our goals? Well, we're going to, first of all, connect to relevant applications. I think that's very important because you need to know kind of what your problem is and then see how it's solved. Select whatever survey we're going to want. Use the apps to explore and ask questions, and then show success in a case history. So here's how we're going to do it. And electromagnetics, I have never seen actually done quite this way, because what we're going to try to do today is do the whole gamut. So we're going to look at all aspects of EM. And by doing that, I think you'll get a different feeling for where different parts of EM fit into the whole spectrum of things. So we're going to start at the beginning, DC resistivity, and it sounds like there's a lot of, well, certainly a number of people here who are really perhaps experts in this field. We'll then look at fundamentals of EM, just to make sure we've got that under our belts. Then we're going to look at inductive sources. So this is where we just have a loop. And we'll look at grounded sources, where we actually have a generator attached to the ground. Look at natural sources. How many people have heard of magnetotellurics? Anybody have had any experience using it or made use of it in any way?
Results of it.
Pardon me?
Results of it.
Yeah?
Final results.
Mm-hmm.
So I've been given final results, yes.
And do you have a good understanding of how those results were obtained? GPR, so that's at the high end of the electromagnetic equations. Induced polarization. How many people are familiar with IP, or induced polarization? And with the future. So that's what we're going to do. That's a lot of stuff. It really is. Trying to pack all of electromagnetism into one day is kind of an ambitious schedule. So there's a wide variety of backgrounds here. But there's also a few people, Hans Rudy, for instance, who's an expert, but we're not really targeting directly at the expert. However, even for Hans Rudy, I would say that I'll offer the following quote. So we go to coffee every Saturday morning. Have a group of people. We go have a local coffee shop. We go there every Saturday. Meet the same people, tell the same jokes, but we've been doing that for 23 years. And when you go into the coffee shop, there's always a quote. And this one day I went in, and there was a quote by a gal named Doris Lessing. And basically is this: that's what learning is. You suddenly understand something that you've understood all of your life, but in a new way. So even for those people, who are pretty knowledgeable in things like DC resistivity or whatever, maybe there's still yet a little bit of a wrinkle that kind of helps you think about things in a different way. The DISC is a 2-day event. Today is sort of the DISC course. It's sponsored by the SEG, and they have a registration fee. Tomorrow is DISC Lab. It's sponsored entirely by the Geophysical Inversion Facility. And our idea there is that we want to capture local applications where people are working on with respect to EM types of problems. and then share them on the web. This has been very a very important part of our tour. We just got back from Vienna, and we had, there must have been 14 or 15 people all actively working on different kinds of EM problems, from environmental to exploration. And there was a lot of serious scientific exchange that went on. Our tour, about 30 locations worldwide, and we're hoping to capture the geoscience problems around the world. The idea with that is that if we go to each place and find out, okay, what kinds of problems are there, how are people attacking them, where is the electromagnetics, how does it all fit in, then by the time we capture them and we go around the world, then it's like, this is a great resource. So we go to India, for instance, and there's this host of problems that they have, which is very different than if we go to Indonesia, or we go to Australia, or if we come to Zurich. But then, you know, at some point, if we've captured these, that'll be a resource that you can see, oh, there's somebody else out there that's working on my problem. Or if you post your problem, somebody says, hey, I know something about that, maybe we can work together. So build a community. And you can connect and work. So one of the things, how many people have used Slack? Anybody? Yeah, so one person. So this is kind of a web-based communication tool that just allows you to interact, ask questions, post comments, and you're invited to join. And then you can contribute to EM GeoSci, use some case histories and content, and also software development, simply. So tomorrow, I guess, tomorrow on Disk Lab Day, we're going to talk a lot about capturing the case histories, but we're also going to talk, and again, it kind of depends on the audience, about SimPeg and looking at the apps and just trying to open up things. How many people here use Python programming? Everybody use MATLAB? Or? So I'd like to give you just a short introduction to EM, just before we just to kind of set the scene. So here's 3 problems that we can concentrate on: mineral exploration, unexploded ordnance. I guess you don't have very much of that here, although you might have some from trying to dislodge glacier slides, right, or snow slides. And then water. So water issues everywhere around the world, we have that. So the physical properties that we're interested in, one is electrical conductivity, the ease with which rocks can pass electricity, or resistivity. I'll spend most of my time talking about resistivity. They're reciprocals of one another. So if a rock does not pass electrical current easily, it's very resistive. So you can get rocks of like 100,000 ohm meters. You can also get rocks that are very low resistivity, let's say 10 to the minus 2 ohm meters. So over here we have sulfides and graphites and salt water. Over here we have metamorphic igneous rocks, stuff like that. A lot of things that we're interested in between fall in that more like 10 to 1,000 ohm meters. The reciprocal of resistivity is conductivity, and it's in Siemens per meter, or sometimes millisiemens per meter. And we tend to use, the electromagnetic people tend to use resistivity and conductivity interchangeably. You just have to remember that one's reciprocal of the other. Electrical permittivity, or normalized dielectric constant. This air is just unity on this. Then there's fresh water, which is 80. So water is the big kid on the block, and most of the other materials will fall in between those two ranges. So this will become important when we talk about GPR, and it plays a lesser role in a lot of the work that's done at lower frequencies. And then magnetic susceptibility, again, can vary on a logarithmic format. The big susceptibility is magnetite over here. Materials that have very low susceptibility are sediments, maybe metasediments, and a lot of stuff that we're interested in actually. So there's 3 physical properties. In general, the way we're going to obtain information about them is we have a source, we input energy, so we've got conductivity, and then those we're going to measure some fields from this experiment. So source, and we've got some data. So Maxwell's equations look like this. This is basically a non-mathematical course, but we are going to at least look at the equations and talk through these guys so we get an understanding of what they are doing. There's the first one called Faraday's law. Basically, that tells us something about the relationship between a time-varying magnetic flux and an electric field. Ampere's law tells us something that if I have a current, then that's going to give us a magnetic field. So these are the equations. We also have from the laboratory work constitutive relationships that relate fields and fluxes. So here's one called Ohm's law. So it relates the electrical conductivity to a current density through the use of a physical property sigma. You notice these numbers, or these letters here, are all in small case. These letters are in capital case. These are in the frequency domain, so I've basically taken the Fourier transform of these guys. We'll be fairly consistent with that notation. So because we're going to be talking a lot about, are we in the frequency domain or are we in the time domain? So let's just start to look a little bit at what we might have. So here is our generic experiment, our source, and we'll put some energy in. So what do we have for sources? Well, we could have an inductive source. We could just have a loop of wire sitting there, right, with current. Or we could have a grounded source. So those are 2 different types. Have a source? Well, what kind of a waveform are we going to put in? Well, we could have a harmonic waveform, something that just single frequency, or we could have a transient or time domain waveform that looks like that. And this could be arbitrary shape, but often it's kind of on time and off time. And then lastly, there's a location. So we could fly the transmitter in the air, we could put it on the ground, we could even put it in the borehole. So there's quite a few options with respect to sources.
So transient means it's switched on and off.
Yeah.
And harmonic, it's
well,
running all the time.
Yeah, so harmonic usually means it's just at a single frequency, and then the transient, most times it's gone on, and then they turn it off, and then they leave it in the in the off time. Yeah, or you could have any kind of arbitrary waveform. We'll see a couple of examples. Okay, so now the next question is, which field do I want? Right, because I'm going to measure some data. So I got fields. I could measure an E, electric field, magnetic field, or either of those 2. And which frequencies do I want? Low frequencies, high frequencies. In time domain, it's really a question of, okay, which times do I want? So that signal is divided up into time channels. So the way in which I'm going to measure an electric field, I'll just put a voltmeter down here, patch it in, so put in 2 probes, and then I can also measure 3 component magnets. So which fields, which frequencies, and then also what components. I mean, sometimes you just need to measure an electric field in one direction or a magnetic field in one direction. And also, where are those data recorders going to be? Are they going to be like in the air? Some of them will be on the ground or inside the ground. So there's, again, a lot of options. So we've got 3 problems. Interestingly enough, electrical conductivity is really important for each of these, for minerals, for unexploded ordnances, or water, just 3 team bucks. So we're going to recognize that electrical conductivity is a major role, and that's what we're going to spend most of today looking at. So with that, I'd like now to switch and actually look at the DC resistivity problem. So I would like this to be pretty casual, especially since it's such a small group. We've got lots of opportunities here. So DC resistivity survey. Everybody was taught, or sometimes it's called ERT, electrical resistivity tomography. There's quite a few people here who seem like they know a lot about this. So, but there's also people who don't. So we're gonna just take it right from the beginning. So here's our DC resistivity experiment. We've got a source, input energy. We're gonna look for the resistivity, and we're gonna do that by measuring some data. So why resistivity? Well, there's a whole host of areas in which it's useful. Mineral exploration, that's a big one for us. Water, inflow in mines, oil and gas, groundwater problems. Here you might have slope stability problems that you can also work on, and lots of geotechnical problems. So those are just a few. It can be used in a whole bunch more. So the electrical conductivity, we've already talked about it, varies over many orders of magnitude. The important thing here is that the conductivity of a rock varies by quite a few things. First of all, it depends upon the rock type. And then, so here's a rock scale, and here's a penny, cent. And you can see that, there's different porosities in there. The pores are probably connected differently. Then depends whatever fluid you've got in there, and maybe there's a metallic matrix at the background. So the actual conductivity that you get out of the rock really depends on a large number of factors, which is why, of course, if you know what the resistivity is, 100 ohm meters, say, it could be all kinds of things. Also, if you take a clay or any kind of sandstone or conglomerate, and you say, well, what's the electrical resistivity of that? You find like, oh, it's a couple of orders of magnitude. So there's no one-to-one relationship between the value of the resistivity and what rock type it is. So we're kind of going to go through this. Of the experiment, I want to talk about sensitivity, a bit about survey design, and then give you an example. Here's the basic experiment. I'm going to set it up as kind of a cartoon here, where we've got an overburden, which is kind of low resistivity. We've got an intrusion that's coming up in here. So here's our mineralized zone. That has a very low resistivity. This background here in Gaussian is very resistive, and we're going to try to find this. So how does the experiment work? Well, we'll take a generator, hook it up to 2 probes, and we're going to put current into the ground. So that current is going to flow like this. It's going to preferentially be, its flow direction is going to be altered by what the electrical resistivity is, and it's going to go preferentially through conductors. As it does so, it builds up charges on the interface of this. And those charges, through Coulomb's law, give rise to electric potentials that you can measure at the surface. And we're going to measure those electric potentials with a voltmeter. That's it. This is like the simplest of the geophysical experiments, and that's basically kind of what's going on. The interesting thing about that is like, okay, well, how do we obtain the resistivity from a measurement? Well, if we go back to Maxwell's equations, here they were in the full, in full form, but now we're at steady state. So we're just going to pump a current into the ground, steady state. And that means that all of the things with any time variation just goes to zero. And particularly the first one just says that we can write the electric field as a gradient of a potential. Ampere's law, to state the divergence, tells us this relationship. And we have also Ohm's law, and we can put all of those together and we end up with, this is probably one of the most classic equations in electromagnetic geophysics, the DC resistivity equation, which is basically div sigma grad potential is equal to some source. You see this equation everywhere. Actually, you see this throughout almost all of physics. If you could only solve one equation in your life, that's probably one you should concentrate on because you got a lot of applications. If we have a homogeneous medium, then we can actually solve this and write the potential in this form. So that means we've got an analytic solution for a very, very simple problem. Now let's look at what happens. If I take a current electrode and I put it on the surface of the Earth, then, and if I look at the flow lines, if I look at the currents, then they're going to flow out equally in all directions. So this is what my currents are going to look like. And if I looked at my potential through that formula here, I'd see it looks like this. So it's infinite right at the current, and then it decays away as 1 over r as I go away. I can take this equation and rearrange it to be something that looks like this. And that gives me the possibility of the following. I could go anywhere, doesn't matter. I go anywhere out here, measure a potential back in here, and I'd get a resistivity, in this case 500 ohm meters, which is the actual resistivity of the Earth. Okay, so when you think about that, it's actually kind of cool. Right? You just put a current in here, I could just go measure a single number, and I can tell you what the resistivity of the Earth is. In fact, we can't quite do that because our circuit always has to have 4 electrodes. I need to have a generator, so I need to have sort of 2 ends of my generator hooked up. So I got an A electrode, a positive one, and a negative one. And we're going to be very consistent in all of this as we're having A being the positive current, B being the negative. And we also are going to, so first of all, if we do that, now what's going to happen to the currents? Put a positive current in here, negative current in here, and this is what's going to happen. So you're going to go positive, negative. So I've changed greatly what my current lines are, and they now look like that. If I look at the electric potential from that, now I'm still infinite here, I'm infinite there, but it's changing in between. If I take my measurement, which is now going to be a voltmeter connected to 2 points, and I'm going to always have am as my positive and as my negative, then if I measure that potential difference, I can actually recover a resistivity from that. So essentially what we've done is we've taken the single current and resultant potential, and now we just realize, oh, well, I've got 4 electrodes in here, so the potential difference between any point is just going to be given by this formula here, where AM is just the distance between vector A and M. So that's just a geometric factor. And now I rewrite this. So that means I could take any 2 points now, doesn't matter. 2 in here, 1 here, 1 here, doesn't matter. Just measure those, know all of the geometric factors, put them in here, and I get out a resistivity that is equal to my background. So 500 ohm meters. What's going to happen if I alter that a little bit, and I put in a more conductive region right at the surface. So I'm going to change it now. So before I had 500 ohm meters. Now I'm going to put in 100 ohm meter at the surface. But what are we going to expect that's going to happen to the current? I'm sorry, your name is?
Filippo.
Pardon?
Filippo.
Filippo? Yeah. What's going to happen?
You said more resistive?
No, it's going to be lower resistance.
And it will bend. It bends to deeper, right?
So the currents flow deeper. Anybody else? I'm sorry, I forgot. Joseph? Joseph, what's going to happen to currents?
They'll be kind of channeling actually close to the surface of the floors.
Yeah, so if I put in a low resistivity there, then this is what's going to happen. So currents like to flow in a path of least resistance, and so they're going to flow up here like this, and that's going to alter the potential. So now I measure potential, use the same formula, and now I get a resistivity of 226. So it's not 100, it's not 500, it's someplace in between. And for that reason, we're going to call the number that we get out of here an apparent resistivity, because we're using like a homogeneous space formula, but it's not a homogeneous space. So we plug it in and we say, well, that's an apparent resistivity. Okay? And it's what you kind of think, right? It's more than 100, but less than 500, because you're somehow looking at both sides. So we have an app that you can play with. It looks something like this. It allows you to have layered spaces, put your A and B electrodes in. You can change your resistivities and layer thicknesses, and you can look at the currents, and you can look at the potentials, and you can see, okay, where is everything going? What are the fields? So those are all open source, and you're free to use and free to contribute. So now I want to talk about two things. I want to talk about soundings and a couple of other arrays. So when we talk about an array, we're really talking about geometry. And here's what's called a Wenner array. So we've got currents on the outside, voltages on the inside, and a nice uniformity of spacings. And here's a Schlumberger array where kind of the same thing, but it's real small. So all of these are just any 4 electrode arrays, but because people wanted to have a name for each of these kinds, they've done it. So the things that you'll see are Wenner and Schlumberger. And we're going to use them to generate a sounding. So this is actually going to be a data map. This is going to be a data plot. And on here, on this axis, we've got something to do with the scale length of this array. And on the vertical axis, we've got the apparent resistivity. Remember, that was the number that was coming out. And this is telling you something about horizontal scale of the array. So let's build up a sounding curve. The very first thing we're going to do is put our current electrodes in pretty close together, right? So if they're really close together, I'm standing here, then the current's only go down to Joseph, and that's about as far as it kind of goes. So everything kind of gets tucked up in this top region in here. And if I looked at the apparent resistivity that comes from measuring the voltage, I see it's basically 100 ohm meters, meaning I'm just looking at them. If I move things back, spread them out a bit more, then now my currents are going in to greater depth. My apparent resistivity comes up to 135, so I'm up here. If I move them up more, apparent resistivity is 239. So we're building up here now a sounding curve. So the only thing that's happening is I'm sitting at one location. I have a geometry that's fixed, and I'm just making it bigger. And as I make it bigger, then I'm seeing to greater depth. So that's why they call it a sounding. So in summary, what we have is for sounding curve, pick our geometry, maybe this is Schlumberger, and just gradually expand, and then we build up a curve then that looks like this. An important thing here also to know is that the scale length of the array has to be actually really pretty big in order to be completely determined by what's going down in here. And we're going to see that that's going to be important later on, because if I'm trying to see down at the back, I'm sorry, was it, you're Joseph?
Yes.
Yeah, if I'm trying to see down to Joseph, then I've got to have an array that's actually at least a few times bigger than the distance, than the depth he is from me. So you're going to have kind of large arrays to see.
Do you change your A, B distance, but M and N stays the same, or?
It changes. For a Wenner array, you'd have the same geometry, and there was like an A between each of those elements, and as you make the geometry bigger, everything just changed. You'd move all 4 electrodes. In a Schlumberger, they used to, I'm not sure anybody does this anymore, they're basically trying to just get electric fields, so they'd have A electrode here and B electrode, and they keep the current or potentials, and then they do that and that, and then eventually they decide my voltage is getting too small, and they'd make these guys a little bigger. This stuff is all over the map, and really the adherence to a Schlumberger array, Wenner array, I mean, these days, especially now when you're talking about 3D geometries, really don't play a significant role. You just need to know that where all your electrodes are, and make sure that the electrode spacings are big enough that you have a good potential. So that brings us then to the next point. This is a map of the data. That's not the scale. That's not depth. It's kind of related to that. And that's not resistivity. Although it's kind of related. So what you really need to do is to invert those data. And by that I mean the following. You've got your data, and you need to work with an inversion process that then ultimately gives you back a true depth and resistivity. I guess this is where I've spent most of my life. As far as today goes, we're not even going to talk about that. Basically, what we're going to do is to have a general methodology in which the thing that we're looking for, whether it's 1D, 2D, or 3D, is all represented by a whole bunch of cells that have a constant resistivity, but those resistivities are unknown. And then you're just going to adjust those so that eventually you fit the data and whatever other geologic constraints that you have. So that technique overall is pretty well established these days. And I'm just not going to talk about it, although we can talk about that more tomorrow if people are interested in. But right now, given what we want to talk about for EM, there's just simply not enough time. So we'll accept that we can somehow do this inverse problem. Now I want to kind of come back and take a look for a little bit what I was saying earlier. First of all, so we have a current that's kind of going through here, and I said, well, there's charges that are built up, and then I want to take a little bit more of a look at that. So when we got a steady state, that means that there's a constant current that's going through here. So the current on this side is the same as the current on that side. So if we talked about sides 1 and 2, then it says that the current on side 1 is equal to the same as on side 2. Okay, that's fine. But now we've got Ohm's law, that J is equal to sigma E, so that gives us this equation here. Now, if the conductivities are different, then that means that the electric field on this side must be different from the electric field on that side. So that means as I'm going across an interface, I've got a discontinuous change in the electric field. Okay. So what is it that could give rise to a discontinuous change in an electric field? Joseph, and then it's Cedric. What can give rise to discontinuous change in an electric field?
Because you have current charges. Yes.
Right. So, like it's that first year experiment that you did, right? Where you looked at if I have charges on a plate. Let's suppose I got a positive charge. Then the electric field is pointing up this way, and the electric field is pointing up that way. Okay. So if I'm coming along here, the electric field is like this, and then on this side it's like this, right? So that's the fundamental aspect for the DC resistivity problem. I'm setting up a constant current, and that means that there's got to be a whole bunch of charges at every interface in which there's a change in the electrical conductivity. And once I've got those charges, then the electric field at the surface is just obtained through Coulomb's law. So we can see that now. So let's just take a look at this. So here's an example. So we've got a sphere in here. We've got a current that comes in from A to B. And now notice, look to see what happens, right? So it's a conductor, so the current kind of gets sucked in here. Right? Looks like this. And the extra, so as those currents are coming in, so now in order to take a look at what charges are being built up on here, we can evaluate those because of that change in the conductivity. And we see that the charges that are built up look something like this. There's positive charges as we go from a conductor to a resistor, and negative charges as a resistor. So there's two things here. So here's the currents that are going through. If I looked at the difference between these currents and the currents that just in half space, I'd have what's called the secondary currents. So total minus what you'd have before gives you secondary currents. So they kind of look like this. They kind of look like a dipole. And that's all caused because of these charges that are built up. And if I looked at the potential from those charges, I'd get something. So that's the secondary potential. And that's actually the guy that we're interested in.
So secondary is basically your anomaly. So you have your whole field minus your background, and this gives you secondary.
Perfect. Okay, so now we've got to measure something. Okay, so we're going to try to discover this conductor in here. So let's suppose we got our currents out here, and now we're going to measure this potential. We're going to do it. So the conductor is actually a 1 ohm meter, 500 ohm meter. So here's our currents. Here's our charges. Put a voltmeter up there, and we get a voltage. Okay. Such that when I put it into my apparent resistivity formula, I get 430 ohm meters. So that's not bad. I'm looking for something that's really, it's 1 ohm meter, but I've got all this other background to contend with. And you can see, okay, it's at least less than the background, so that's indicating that there's something that's more conductive there. What happens if I go out someplace else? So let's suppose I go out here. So I'm now going to measure a voltage that is out here, and I calculate that voltage, or measure that voltage, put it into my formula, and I actually get this. It's very strange, right? It's 502. So there's something, so the question is, okay, what is actually happening that I could get an apparent resistivity that's actually larger than anything that's in my whole system? Right? Pardon me?
The air is not still.
No, no, there's something else that's going on. So you can ponder that, because we're going to come back to that because it promotes some extra understanding. Anyway, if I did this, I'd have an apparent resistivity that was 502 or 30, 502. So it would be a curve that's getting low as I go over top of this part. That brings us then to something else that we call, so we had sounding, and now what we're going to do is profiling. So in a profiling mode, I'm going to fix my array, and I'm just simply going to move it across this. What's your name is?
Luca.
Luca? Right. So if I've got everything really close together here, you know, my currents are maybe looking like this. I'm walking right across here. I don't see Luca. I don't see Lindsay. I just see this background, right? So that's what's happening here. If I put everything close together, and then I go across this, I've got a apparent resistivity of 500 ohm meters, which is what that has to be. Now, however, I make the array larger, yeah, and I come over here, and now I'm actually sensing Luca, no problem, right? So that's what's happening in this offset. We get something now. So here's that apparent resistivity, and it's pretty low. Actually, in this case, it's 300 ohm meters, right at above that. Notice also this overshoot here. Now that overshoot's getting bigger, right? That's no longer just a couple ohm meters. That's a pretty significant overshoot. So now the question is, okay, where's that guy coming from? We'll come back. So those are the two things. We've got soundings, where I'm just going to pick an array and just expand it, look deeper. I could also have profiling, where I pick effectively what my depth of sensitivity is, and I'm just going to kind of go walking over. So now that's a translation. There's a whole bunch of different arrays that one could use. We talked about these two guys. You can also have a gradient array, in which you just generally put out two probes for the current electrode, and you just measure the potentials everywhere in between. You'll hear of many things like a pole-pole or a pole-dipole or a dipole-dipole. Where's all that stuff coming from? Well, you basically always need to have 4 electrodes, but if I took one electrode and just ran it, you know, let's say I took the other current electrode and just ran it a couple of kilometers out this way, then I'd have a pole-dipole experiment. And that's done. I'll show you an example actually later for mineral exploration, where it's exactly what it's done. You just run this out a couple of kilometers, put stake in the ground, and then you go. So now let's think about this kind of profiling sounding thing, and you have to contend with plotting the data. How many people have ever heard of a pseudo section? 1, 2, 3, 4. You guys are so shocked. Wow, of course, Andrew. Okay, you. Okay, so pseudo section. We've got some data. And we just want a way of plotting it, right? No big deal. Let's just somehow plot the data. If we could plot the data in a way that conveyed some information, that's good. Otherwise, it's just a bunch of numbers. So what we're going to do is we're going to take a transmitter and a receiver, and we're going to plot the data on a map. So everything is kind of, the array is going to be going along this way, and we're just going to plot it on a map. And the way that we're going to plot that is that we're going to make 2 45-degree angles here, and where they intersect, we'll plot the data. So if we move this potential electrode out farther this way, then they intersect here, or this way, they intersect there. Right? So somehow in the idea of this, as the distance between a transmitter and receiver get larger, then we're going to be plotting farther down the paper. That's it. So what we're going to see here is a profiling sounding curve in which this guy is start out here, he's going to move progressively out, and then we get this line of data. He's going to go over here, same, and then we'll gradually build all that up and contour. So you see how we're kind of building up this pseudo section. Okay. So we've gone along. Each point calculating parent resistivity. These are 30s. That's 400. So the red is low resistivity, the blue is high. There's information there. So you know something's happening, but it's just a way of plotting the data. So unlike seismic data or unlike GPR data, where you look at the data and you can see structure and you get things, you can't do that. Not even in even fairly simple cases. The simplest possible case that you can even think of is this. If we take so this is a conductive block in a half space. I do BC survey over top. I get a pseudo section that looks like this. So it doesn't look like that. It's got sort of pant legs on it. Still, there have been occasions where people, when you recognize that, say, "Oh, I think there's something right here I'm going to drill." And they may have been lucky. Here's a case where there's no hope, right? Take the same case, put on some little conductive blocks up here, and the pseudo section looks like that. So there ain't nothing there compared to the eye, right? That's just a picture. This one's a bit more interesting. Well, I'm not sure, very interesting. So here's section, different conductivities up the top. There's basically two buried conductors in there. Those are the guys that you want. And if you calculate the apparent resistivity pseudo section, actually it looks kind of similar. It looks very simple. It looks like this. And you see a major, major anomaly in here. If you actually went and drilled this guy here, you'd actually drill right through here. So it's conspired so that where you think is the region of radiation anomaly, there ain't nothing there. So you need to invert the data. This is stuff that we've been doing since 1990, I guess, or a little bit earlier. We're going to do the same process. We're going to invert those data. And now let's see what we got. So if we go back to that prism, here's our pseudo section. Now if we take this and invert it, we get something that looks like this. So this is actually pretty good, right? We've got kind of a localization of this conductor. And certainly if we drill through here, we'd be in good shape. We don't have a blocky representation here, but that's because of our inversion code. We're just looking for something that was smooth. You can easily put on a different norm and get out something that's blocky. But the bottom line here is that even just kind of working with a smooth norm inversion, you get out something that is actually pretty representative of what's there, and that is geology. If we go to this case, where we had a little bit of clutter up here, and you invert that, not only do you see the block here, but you actually also see the clutter. And actually, maybe that clutter is interesting to you. That's just, it's small structures that are happening near surface, and you're actually able to pick that up with a DC resistivity survey. And finally, with this GIF model, got these two conductors, resistivity section, and then invert it, and now we've got two conductors. So they're both in about the right place, and so you've been able to unravel it.
Can we go back? All your examples show us recovered resistivity rather near to image. Is this normally the way, so you can't focus them?
There's quite a bit that you can do with tailoring the inversion algorithm. Certainly, if you feel this is not quite the right character, you could change. These are all L2 norms on the derivative of the model. And you could change that to an L1, which could give you blocky, or you could even go towards L0, which would now give you like the most compact body. So as you know, as more and more information about the type of geology is obtained, it's easy to kind of have those modifications put in, and so you can get different results. The other thing is that you might know something about the background resistivities. You can go ahead and invert that, put upper and lower bounds on each cell, and lots of flexibility. Okay. We're actually just not going to talk very much about that, but this, I mean, I think this is kind of remarkable in a way. Like you could have L2 smoothing, so you're minimizing the L2 norm of the derivative of the model in the X and Z direction. And let's go back here. Yep. So you're asking for something that's kind of smooth, and you still have kind of recovered the essence of what there. And if you know what your inversion algorithm is giving you, so that like, okay, I've got a sharp interface, but it's never going to give me a sharp interface because I'm using L2 smooth. Then you start to kind of mentally interpret it. But L2 smooth turns out to be very robust. If you then start to change your model norm, especially as you go to L0, things can be a bit more challenging, and it's easier to get you know, extra artifacts. Okay, the world's 3D. This is where we're really at. We've got a host that's complicated. Yeah, we got topography, variable background resistivity. Our targets are complicated, okay, of both the shape, size, depth. So now there's a question, right? So you've got this body that's buried in there. You've got lots of topography. What do we do? Where should I put the currents? Should I use a 2D acquisition, a 3D acquisition? Where do I take the measurements? Which measurements? What's the effect of topography? Perhaps this is an area where ETH has really distinguished itself over the years in developing, fundamental, use of the pole analytic solutions, or that they are in fact the primitive solution for the problem, and to then design efficient ways of trying to collect as few data as possible that gives you the maximum amount of information. Even despite that, it's still a challenging problem. You go out into the world and you've got a complicated environment, just trying to figure out, okay, which currents, where, and how often. I think, at least for most of the people I know, we still struggle with that a bit. It's not a slam dunk, and each problem that we have requires its own careful query. So these are all questions of survey design, but the bottom line with survey design is that there's the basic element is sensitivity. Okay, so if I'm going to ask for a definition of sensitivity, what's the, give me a definition?
Well, maybe that's spontaneous.
Especially in the context of an inverse problem. What do we mean?
I mean, on how much my solution changes if my data changes slightly.
Yeah. That's I wouldn't put them quite in that order. I'd have kind of gone the other way around. But for sensitivity, from the point of view of the inverse problem, we're trying to find this guy here. So there's some maybe parameters associated with it. Maybe it's the resistivity of this versus that, or maybe it's some kind of a shape here. if the measurement that we're having is sensitive to the body, okay, then a change in that parameter will give us a large change in the data. So I mean, it's essentially what you said. So that's really what we want to know. What's the change in the data if I changed this parameter, right? Because I want to see, I'm going to postulate a measurement, and now I'm going to change a parameter. Do I see anything or not? Right? If I do see a large change, then I'm sensitive to that. So that's what we need. We need to have sensitivity. But what I'd like to, generally people don't, well, maybe, I'm not sure. My experience is that people often just jump, like, okay, I'm kind of working, what's the sensitivities? But I think it's actually easier if we take that issue of sensitivity and divide it up into two parts. The first is the need to excite the target. Forget about the data. If we're going to do something, we've got to excite the target. The second point is then we need to have a sensor that's maybe close to the target and the right orientation so that we see something. So we're going to do that with this example here. So here's our A and B electrodes. Here's our current that's coming through here. These are secondary currents or charges that are built up. And you can see by doing this, we've definitely excited the target, right? So we got large negative charges here, positive charges. So we've excited that target. Good. That's part of the target. The next then thing is the measurement. Well, given how we've excited the target, and given that we understand where to go, I mean, clearly, if we're going to put potential electrodes in, we just want to get them as close as possible to these these charges. If we're, if we could possibly go down hole in a borehole, it would definitely be better. If we're sitting up here, then we're sitting up here. So that's sort of the measurement aspect of it. Another important thing, we're going to see this throughout the whole day, has to do with coupling issues. So I've got a thin plate here, a number of different potential orientations. So it could be sitting this way, or it could be horizontal. So how does that, what do we do with respect to the excitation part of that? How do things go? Well, if I have the plate vertical, like this, and drive current through it, you can see, like, okay, there's stuff that's coming in. If I have a horizontal, so there's not really all that much change in the flow lines. If I have a horizontal, though, look to see what's happening here as far as the flow lines. So you've really greatly altered what those current paths are. So even though you have a particular source, if I move my target of interest a bit, change its orientation, I'm clearly going to couple with those primary currents in a different way. So coupling is definitely going to play an important role. The other thing that,
Question.
yeah.
If you think of, say, third body, it would be the opposite. So you have your plate, but it's then high resistivity, yeah, and you could have, say, a vertical intrusion as a similar body. Yeah? So in this case, you would be with your geometry, you would be more sensitive than to your intrusion than to your oil layer.
Yeah, I mean, there's aspects of that could certainly be that could be looked at. If you have, basically, you're talking multiple bodies here, right? You've got something that looks like this and something that looks like that. Is that what
or
pardon me?
Or.
Oh, so but then it's a question of whether it's resistive or conductive. Is that?
No, so you are looking here at the conductive body. If
yep.
you're looking at a resistive body, like, say, carbon layer or and vertical intrusion.
Well, let's just take the first part of that. Okay, so you can see these are conductive bodies, right? You can see how the currents are being pulled in. What's going to happen if, if I do a resistive body?
current is going to take a detour.
Currents are going to take a detour, right? So things are clearly going to happen if I have a conductive body versus a resistive body. If I do a resistive target and a conductive target, here's what happens. So now I would take this vertical cut here, right? And so here's where it's a conductor, and I get charges. So the charges that are built up here. If I make it resistor, you see how the currents are excluded. And look at the magnitude of the charges. So on that resistor, for this particular geometry, we're actually much more sensitive to the resistor than we are to the conductor. I think that's kind of where you were going. Right? So you can start to see how things are kind of coming into play here. We got coupling, orienting the bodies, but then you also have whether it's a conductor or resistor. So in summary here, we've got talking about sensitivity. We need to drive currents into the target. So we also need good coupling. For measuring the data, want to be good proximity to the target, and also make sure that we've got sufficient, or have to worry about the orientation and separation of those potential. And background resistivity is important. We haven't addressed that yet. I'm going to come. So here's our questions of survey design. We've got the first is, okay, what's the objective, right? And if you've got a layered Earth, no problem, do a sounding. If you've got a 2D Earth, then you've got to do both a profiling and a sounding. And you're going to want to do this perpendicular to the geology. And if you've got a 3D body, you need 3D coverage. And then you also have to worry about the background, resistivity, and then all the noises, the fences, the power lines, and stuff like that. So those are now we're getting into more of the real kind of practical nitty-gritty questions. The general question of survey design, however, is one that it really has to be solved on a problem-by-problem basis. And the only general way that I know at this point is really just to go back and appeal to numerical simulation. For instance, in this guy here, let's suppose we got this target. It's coming here, we got this background. You first of all need to design this geologic model, assign your physical properties, select a survey, and then you do two things. One is you do a forward modeling simulation with the target and without the target. That's it. Just do it. Without the target, maybe it looks like a dash line. With the target, it looks like this. And now you assess this difference in the value of your datum. And then that's what you're seeing as far as the difference. The question is that big enough? It has to be big enough. And there's two metrics that you can use. One is that has to be greater than some floor value, which will again depend upon your circumstances that you're doing, and generally also a certain percentage of your primary field. DC resistivity experiments, for instance, the work that have always done. Yeah, we usually start off with probably 5% uncertainty in the voltage measurement. And maybe a floor area. So we might actually have uncertainties that were assigned to the data for the inversion as a certain percentage of the datum plus a floor. But every problem is different, and you have to make use of what you've got. So I'd like to give you a short case history. It's a mining project, but I think everything will kind of carry through. And sort of show you an example. I'm going to parse it down into those 7-step procedures. So this is an area in Australia It's called Mount Isa Mines, MIN. And we're going to parse this through in that 7-step procedure. Here's the geologic model. It doesn't matter from your perspective what these things are. They're all kind of color-coded. These are different geologic units. There's a couple that are kind of important. There's a mineralized body that we're going to try to find in there. It's a talk about physical properties later, but it's a conductive unit and it's buried in some siltstones. So there's some volcanics here on the outside. There's also a shale unit in here, and there's some siltstones that are in here. So there's volcanics, shales, siltstones, mineralization. Our question that we're really asking in the setup is that, can a conductive unit, okay, that's in these siltstones, can we identify that with the DC resistivity survey? So at this point, and we're going to change things a little bit later, but at this point, we're only going to be thinking about electrical conductivity. So what are our properties? So here's those different units. And we need to be sure if we're designing a survey that we're different from other units. The thing that we're looking for is this thing here. It's called the Mount Novit horizon, and it's got a high conductivity. That differentiates it from some volcanics, which are low, and also some siltstones, which are moderate. Okay, so that's good. The thing it doesn't differentiate with, there's this thing called a breakaway shale, and that's very high conductivity. Okay, so this is good. So we're gone into a region. We're trying to decide, what the physical properties of this thing is, and we realize, like, okay, first of all, it's quite conductive compared to any siltstones or volcanics that are there. So and it should be buried in the siltstone, so we might be able to find it. But there is one other unit out there that has a very high conductivity. So the thing that we're not looking for is not the absolute highest conductivity, but something a little bit. The geology here, I'll go to this next one, is more or less north-south. So it's almost kind of a 2D geology. And for that reason, you could think about doing, remember, profiling sounding curves across here. So they did 10 of them across here. So 10 individual sounding arrays, but we're going to put it all together into one 3D inversion. So 2D acquisition, 3D inversion. So what do we get? Well, here's our apparent resistivities. So now this guy should look familiar. It's a pole dipole. Remember, to get the pole, we just had, ran this current electrode out a couple of kilometers on that side. So here's what the pseudo-sections look like. Remember I said that was just data, ways of plotting data. You do see something that's coming in here. There's some higher conductivity, so there's something interesting that's going on. But you also remember I talked about excitation. This is all with a single current on the left, right? If I change where the location of the current is, I'm going to ignite the Earth in a different manner, and that should give me a different complementary data set. So I'm going to now make this following. I'm going to put my current on the right. Now you can see how much I've changed the images. Here's my parent conductivities. So now I've got something that's really kind of big. Nevertheless, that's still just 20 maps of data. There's one 3D conductivity structure out there that we're trying to get. That's got the geologic information. So let's see if we can find it. So to do that, now we're going to do the same thing I talked about earlier. We just generate a 3D mathematical model of the Earth, divide it into a whole bunch of cuboidal cells, and yeah, sort of adjust those until we get something that fits all 20 of these pseudosections and has got some reasonable geologic structure. But actually, I'm actually quite proud of this. This was the, I believe, the first 3D inversion of DC resistivity data, certainly for mineral exploration, that was done. We did this in the late 1990s, I guess. Started to be a long time ago, mid-1990s. And we've revisited that recently. But this is kind of what came out of simply doing blind inversions of this DC resistivity data. And the mineral companies were absolutely ecstatic about this. So what you're going to see now is it's a cube of conductivities, and we're just going to portray that. We're going to slice in and out, and then we're going to slice in plan view down, and then we're going to rotate the image and look at progressively larger isosurfaces. Oh. Now we're slicing in and out, and the red is conductive. Blue's resistive. So now it's, we're just changing the isosurface. Until we're finally left with this. So there's one big, long conductor that's sitting up here, and then there's maybe a little guy out here, and maybe something. So in color coding, it looks a bit more like that. So what's our interpretation of that? Well, this region that's coming in here, we're identifying as that breakaway shale. So, you know, this is a wonderful geologic image, and it's converted geophysical data into geology. And the major unit here is this guy here, this breakaway shale. The other things that we see is that there is a hint back here of an intermediate conductor. So it's a high conductor, certainly compared to anything out here, which are volcanics. And it's this guy here that is kind of potentially of interest that looks like it might be, might potentially be the mineralized zone, because it's definitely higher conductivity than any of the stuff in here. But it's not the highest conductivity. So that's actually where we're going to leave it at this point. And I'm going to come back to the same example as the very last thing that we do, because the sort of the physical property that's of relevance here is not only the fact that it's conductive, but also there's chargeability that's associated with some of these rocks. And we're going to look at the the induced polarization that comes, the IP effect that comes from that mineralized zone, and we'll see that that is actually going to clean this thing up, and we're going to get a really sparkling interpretation. But we first of all, and whatever, we certainly needed to get that DC resistivity component out, and we've done that. Yeah.
I have a question back to here views. So you have used the 2D data acquisition for getting a 3D model.
Mm-hmm.
So to what extent do you think that this has influenced the inversion image? So I mean, in a perfect world with unlimited budgets, we probably would have deployed, you would have deployed a 3D or a 2D deployment in order to do a full 3D inversion. So to what extent you may get some artifacts or small flaws in the images due to the acquisition geometry?
Yeah, that's a pretty tough question to answer without actually having, having done that. But Hans Rudi's point is really well taken, right? So we're just looking at data here. We don't have any currents here, currents that are going across here and measuring potentials elsewhere. And things are complicated, especially up in this region in here. So unquestionably, we would be helped by having a better data acquisition. This is pretty minimal. This was actually pretty much at the leading edge at the time that this was done. But I think nowadays we'd look at this and we'd say, well, at least we want, even though we kind of, fairly certain that it's more or less 2D, we would want to go out with some kind of 3D acquisition so that you get some better understanding of what's going on. The place actually that it comes out is, as we'll see in the afternoon, there is regions up here that are actually pretty complicated, and having a better strategy for acquisition would definitely have helped.
Oh yeah, I was bringing up this point because many people here are from seismics, and particularly from characterizing the surface, we are often faced with the problem that we have a few sparse 2D lines and need to get a 3D image out of it. And we know with seismics that this is quite a bit of an issue. However, with geoelectrics, we have talked about these sensitivity curves, which can be quite broad, and it's just kept left wondering as to whether these broad kernels, which also extend quite a bit away from the acquisition line, might be helpful for geoelectrics, so that such an approach would be more justified for potential field methods like geoelectrics compared to wave field methods.
I think we're kind of halfway in between. So if we have, especially if we have a pole current here, right? Then that current is going out, but at the same time we're only measuring potentials along here, so that is very limited. So there's a little bit of a robustness here with respect to DC and IP that you can sometimes not do full 3D acquisition and still get out something that's useful. But this whole situation, I'm sure, would be improved if you had done 3D. So we've got some very valuable information at this stage. We could do better. I have a case history here. I'm probably going to, I'll just kind of show you what this is. Let's see. This is a case history that we have just put on, and it's actually in the use of self-potentials for monitoring dams. I don't know, is that something that's done here at all in Switzerland?
Yeah, we did some along the river tour, yeah. Actually there, so that was mostly to see interaction between the river and the groundwater. Yeah. But most of our problems were actually variations in the soil moisture. So that was our main.
Okay.
That we saw.
What about dams? Do you?
Well, we have plenty of dams, but they are not yet monitored with self-potential masts.
So this is actually work by Ravel Valera. As they're looking at dams, and then the idea is that you get water that flows through through a dam, and you get streaming potentials that are generated. And basically, at the end of the day, you've got charges that are built up on both ends, and that gives rise to a self potential. And yeah, so this was a dam in France where they did a survey and measured self potentials and all over the whole area, DC resistivity lines across there, and then we're able to both capture the self potentials and then went ahead and inverted the data. That involves taking the self potential data, finding out the electrical conductivity. You do that from the DC resistivity survey, and then you need to do an inversion to calculate the streaming currents. So that's the procedure that's done. The inversion.
Just a question. So you are seeing the flow, not the water.
You're seeing the flow. Right. And ultimately, after having inverted the potentials to get the streaming current density, end up with a map that looks like that. And now what they really wanted to do was to get that into a flow. Actually, tried to find the flow velocity that took the streaming currents, and then they needed to have this charge build up, or the sort of volumetric charge per unit volume of the material that's in there. You can work with lab material and get up a relationship. And then now they've got both JS and Q, then they can get the velocity. And then from that, they were able to show that in here, you could actually get a fluid velocity of 3 × 10⁻³ meters per second, which ultimately gave them a flow through the dam of 3 liters per second. That's a moderately involved case history. We could talk about that tomorrow if people are interested, or those are captured in the slides at this point, and the paper is there. So it's just one of those kind of nice examples of the use of not so much DC resistivity, but actually, charges and how it's manifested through an electric potential and then inverted to give you something. What I want to do now So basically, we've kind of done this background, had case history on Mount. I want to return to this issue of background resistivities, because we're going to take that same example that we just had. So here is our conductive model, and we put our A and B electrodes in here. We've got currents that are flowing in here. What happens if we put on, and what we're going to do is put on a conductive or a resistive layer in here. Okay, so let's think about that. So let's put on a resistive layer to start with. So I'm going to just put on something that's very highly resistive and put that just above the sphere. So what's going to happen?
Yeah.
Feel?
Yeah.
So we're going to put in a resistive layer above there. Here's the currents. Without that, what's going to happen with?
We have another resistance layer on top of the sphere.
Mm-hmm.
Is the current lines trying to get away from the resistance layer and going to be all even more so through the conductive sphere.
So the current lines get refracted and then funneled into the sphere?
Is the resistive layer covering the whole?
Yeah,
I mean, how large?
Yeah, we'll just put a resistor layer on top.
Well, then everything stays. And there's another conducting layer above the resistive layer, or is it all the way through?
No, it's just it's a homogeneous half space, 500 ohm meters. Got a conductor in here now. I'm just putting in a resistor. We just want to start to explore the effective backgrounds.
Creates a shadow.
Pardon me?
It creates a shadow then. You would not be able to penetrate it, and you need a much larger body to create the same amount.
Okay. Any other thoughts? Got two different ones? Okay, back row, yes.
So, yeah, if you put that more resistive layer on top of the filter, you probably be able to see it with curve to be that so deeper than
Okay, yeah. So,
yeah.
This one?
I just thought it's going to be hard to get any current in the ground. No, I don't really know.
Yeah, well, I'm not. We're not changing the resistivity right here. Yeah, so we can get current into the ground. That's not a problem. It's not like we're in Chile and we have a whole bunch of bleach in. Just can't get the damn stuff in. Okay, shall we look? It's a resistor. You people, I mean, you're talking about currents refracting, but currents simply do not go through a resistor. It's like it's infinite resistor. The currents just get confined here. This picture is a little misleading because it actually shows like there's stuff in there, but the amplitudes here are extremely small. This is the 10 to the minus 1, that's 10 to the minus 6. So the currents above a resistor just stay above a resistor. And look at my apparent resistivity, it's 1652. So I was looking for something that was, without a resistor it's 430. Now it's put a resistor in at 1652. So to show how ineffective this is by the conductor underneath here, here's an example where I just have the resistor do the same thing. So the currents are basically the same, and I get the same resistivity, 1650.
So you create a shadow.
You create a shadow. You're exactly right. There's no, you got current, sees a resistor, can't go, got to go someplace else.
If this was your target was a high resistivity body,
Wouldn't matter.
would be the same.
I'm completely shadowed. I don't care. I can make this infinitely conductive or infinitely resistive. It's hooped, right? So this is the important about background with DC resistivity, is that if I have, a resistor, even if I just have a thin crack of air or something someplace, right? You're just not going to get current that goes through there.
Interesting. We just recently had exactly the same problem. So in the Barents Sea, there's source rock, so-called hacking shale, at very shallow depths, like 400 meters or so. And this is like good source rock, high resistivity layer. And going through it is incredibly difficult. Yeah, and it that's the word. So anyhow, so you have problems to identify targets below.
Absolutely.
Yeah.
Absolutely. So this is like one of the big,
So I guess the picture would completely change if this resistance layer was extended all the way to the top. I mean, let's say there's still enough coupling to get energy into the ground. But if this was not a 3-layer, or it would be half space in a 3-layer, but a 2-layer system.
Yeah.
Then I guess this refracting further down have larger sensitivity, larger depth would occur, right?
Yes, and you can experiment with that yourself because there's an app. Okay, so we're providing you with an app for exactly that question. Okay, so you have a what if question. What would happen? And the way to really get some insight about that is to ask that question. You have an app, and then you just try it and see what happens. Okay, so that's our resistor. What happens if we made that resistor a conductor?
Same thing.
Anybody else?
Yeah, same thing.
Same thing.
Also focus.
So we have a conductor. Now all current flows through the conductor, and you still don't see it. So you've effectively screened this big conductor that you saw here before with either resistive or conductive layer. So what we're going to do next, we're going to break for coffee, but what we're going to do next is we're going to show you that if you have this resistive layer or if you have a conductive layer, under what circumstances you could actually see through that with an electromagnetic survey. So in order to do that, we're first going to come through with the fundamentals of EM, and then we will do, do the fundamentals of EM, and then we're going to do inductive source. So it's going to be a little bit before we actually get to this. But then this afternoon after lunch, we're going to come back, we're going to do grounded sources. And when we come back to grounded sources, we can actually look at the effect of this guy. Okay, good. So I don't know, what do we, there should be coffee here. What do we do for getting a cup of coffee, or at least, you need to stand up and stretch your legs, and then we'll do the fundamentals.
So how long do you want to have to break?
I don't know, 15 minutes. Okay.
Do you want a coffee? I can find something. I don't know.
I will leave for lunch, so don't be afraid if I disappear, because I'm first floor, and I will be back right after 1 p.m. So
Okay.
I will step in. For the coffee, we can go down to this machine.
Perfect.
Or Tanba.
It depends on the budget holder, so on the
Yeah, I just
invite.
wanted to say the same. Thank you very much. It's really informative.
Are you leaving?
Just for before lunch. Because I have a doctor's appointment and I'm going to come back.
Oh, you're going to miss the fundamentals.
Yes, exactly.
Oh, no.
Sorry. But yeah, see you later.
Yeah. Okay, so let's go for coffee.
Yeah.
Flipper, are you locking the room if you go out?
I will do that.
So you say you
Okay, so we can leave everything here.
Yes.
Well, I don't have a key, but okay. You
good modeling now.
No, it's the one I did here. So we do everything.
Partial differentials. The instruction that said because of the if you have a cap layer which is a very extremely large or small conductivity, and then you cannot observe this little ball. So that's why we use EM.
Yes, because that's EM. Yeah. But you probably use the layer as a sort of it's changing current. I mean, it's one here, one is a static current, then just
Yeah, but I also think about if we do the modeling to the to this structure, which has a very large or extremely large or small resistivity, and then we do the full modeling to this.
the same structure, but you have a ball. But this one is very low resolutivity. But, so if the data, we do a full modeling, if the data that are different, we then do the subtraction, and then we use the delta D as the input. Yeah, but you don't see this. No, what we want to invert is just this one. Nothing here. We just invert the delta D. So you have D1 and D2, and we use the delta D as the input, and then we want to invert for delta M. And then we call this one as M0, delta M, this one the M1. M1 equals to M0 plus the delta M. But you will never see this. There's no data for that. I mean, the data is from here, it's from delta D. Yeah, well, we started D1 and D2. I mean, okay, if you have an initial model, which you have this. I mean, if you already have a knowledge of this thing, then you're cheating. Yeah, because D2 is just something like an observer, right? Yeah, but you don't observe this. Yeah, but in the data, even in the data, you don't observe this. Yeah, that's what I'm saying. If that layer shadows everything below, then you have no knowledge of the sphere. Yeah, but just curious, if that means you are saying the D1 and D2 they are exactly the same. Yeah, if these are data, there's no way that you can see the thing below. I'm thinking maybe it's just because it's very, very big, but doesn't mean it's nothing. Yeah, no, of course. But I don't know if the case scenario there is nothing below. I mean, yeah, I mean, no. Again, I'm not an expert, but I yeah, it's definitely going to be quite hard. Yeah, you probably choose something that is maybe very far from the correct amplitude. Yeah, so that would be a concern.
thesis, visa and passport documents and stuff, asking for the resubmission of this PhD thesis and for a job. I don't know what you can find. Person kind of you know, for research. So,
This example, like the one he the data is a tool.
So with the joint work, we base it on Gimli. I mean, well, previously I had my own code in MATLAB, and now we're going for unstructured meshes. So then we're actually using or contributing to Gimli. Yeah, so that will be open source once it's stable.
Nice.
Yeah, then we have some in-house code as well.
Yeah.
But we're definitely aiming at getting things out there.
Yeah, yeah. Oh, it's great. And I mean, then you get feedback, you get more eyes on it and all of that, but it's certainly a big undertaking.
Is he actually recording all the sessions?
Yeah, it's such a helpful exercise. Remember what for other people to be able to, and there's some places where you're not going to get to on this, right?
So afterwards you'll take like one full day from one of the places basically. Online.
Yeah, I mean, most of them are out there. Some of them are very quality, so you know, we try recording in every place, and hopefully by the end we have an integrated page of shit. Yeah.
What she's trying to say is that if I do this 30 times, there might be one place worth keeping.
No, internet connection, sound,
Maybe one.
No, it's cool. I mean,
fantastic.
Yeah. I was saying to Lucy, I mean, I started playing with those apps, the Jupyter.
Oh yeah, yeah.
And it's great. I mean, I'm going to use them in my own course actually.
What course do you teach?
Introduction to Environmental and Applied Geophysics.
Oh, okay.
So,
yeah, because we basically teach the same course. Actually, there's a lot of people that are basically teaching that same course.
Yeah.
Because that's one that's universally
Totally,
needed,
it's
right?
like the first
And
exposure to applied geophysics.
Yeah, and everybody's confronted with the same challenge of trying to assemble material to a whole suite of things. And so we've got some stuff, and then we were talking to
Florian.
Yeah.
Well, we're closely collaborating with Thomas Günther for the. I mean, he's the main developer of the PyGimli.
Yeah.
And so I'm using that, or we're using that a lot for our own research.
But they're like Florian was teaching a course, and on exactly.
On that, yeah. First year students.
First year, first.
Well, I guess
third
year
students.
First year.
Yeah, and so integrating the apps with the teaching, it's a great way of kind of getting people involved as opposed to just standing up and writing an equation or something.
Yeah.
Okay.
We can even show that briefly today.
Yeah, I definitely do that. Okay. EM fundamentals. What do they teach at ETH for electromagnetics? So for people who come through.
Well, I mean, in the bachelor program, there is a course where they really get fundamentals, but really only the basics. And then it depends. So those that are going through the joint master program, so they are tortured with Maxwell's equation quite a bit in Delft from every slot.
Oh yeah, and, it could be torture.
Here at ETH, on the master level, it is a bit more limited. So that is a course of Alexei Kuzhinov on inductive EM.
Oh yeah. Does he have a book, or?
I don't know. So, has anybody attended the class of Alexei Kuzhinov? Okay. So I know that they are also treating fundamentals of EM and also but focusing on most of magnetic theory. So this is my understanding.
Oh, on the MT. Ah, okay. Perfect. Okay. Well, we're going to do everything. So there we go. So motivations. There's already, we've alluded to a couple of things that make it difficult for DC resistivity. So one of them is actually area. Like, suppose you've got 100 kilometers squared to work with, and thinking about DC resistivity and stuff. We saw that a resistive layer shields the target. There's places where it's just simply hard to inject current, and there's also places that simply have a rugged terrain. And these are tough slogs to do a ground-based DC resistivity. So what we're going to do is to look at the potential for using inductive sources, and kind of take you through the spaces. So here's the basic experiment. Probably everybody has seen this, but we've got a transmitter, which is just basically a loop of wire, and a receiver. And this transmitter puts out a time-varying magnetic field, and that produces eddy currents inside a conductive target. And those currents produce secondary magnetic fields that go up to a receiver. So that's basically it. It's a three-step process. But what I would like to do now is to kind of break that down a bit and look at each of those individual pieces. So that's, first of all, the transmitter. So we got a transient waveform, time domain, or a frequency domain. And actually, one of the things that we're going to see, and certainly by the end of the day, you're going to realize, like, okay, frequency domain, time domain, doesn't make any difference. I understand both of them equally well, and that they're really part and parcel of the same thing. If you look in electromagnetic books, at least the way I was taught electromagnetics, the very first thing you do is you see, oh, I take Maxwell's equations, I do a Fourier transform, I look at them in frequency domain. Okay, I mean, it's fine. But then you do all that stuff, and then, okay, then the next chapter, oh, now what happens in the time domain? It's like it's totally divorced. But that shouldn't be that way. And in fact, you should be presenting, in most cases, a lot of time domain stuff first, because it's easier to grab the intuition in time domain. So we're going to blend continually time and frequency as we go through, because there's really no difference between them, and it just makes things really easy to understand.
There is additional information coded in frequency.
Maybe.
I think it's not. It's a question.
Is there? No,
No.
I don't think there is. No, it's just repackaged differently. But if the intuition, I think, is much easier in the time domain than in the frequency domain. And once you've got the intuition, then everything comes in. Okay, we'll talk more about that. So here's our Maxwell's equations. And we're going to be working in something called quasi-static. And the only thing that's going to be, as far as Maxwell's equations, we're going to omit one term in here, which is, this is the displacement current that's coming in here. So B is electric displacement related to electrical permittivity, and its time derivative is displacement current. So we're going to omit that. So our equations in time, frequency look like this. So let's first of all look at our transmitter. And for that, we need to do Ampere's law. So if you're all familiar with this, if I take a wire that's got a current in it, and then if I put my thumb in the direction of the current, then I've got this circular magnetic field that goes around, right? So the current, magnetic field, looks like this. It's azimuthal, falls off as one of our. If I take that wire and I wrap it around on itself to make a loop, then now my magnetic fields look like this. And it's exactly like the magnetic field of a little elementary magnet, a bar magnet. that you'd have that would sit right in the center of that loop. And the expression for that magnetic field is given by this. And the important part is it falls off as 1 over r cubed. And the other, it's got an amplitude here, which is m, which is called the magnetic moment. Magnetic moment for this kind of a system is the product of the current times the area. Okay, so current, have a loop of current, gives rise to a magnetic field that looks just like a bar magnet, and that falls off as 1 over r cubed. It's got an amplitude. Now we got Faraday's law, which tells us the following. If we have a time rate of change of B, so B is the magnetic flux density, Weber per meter squared. By the time varying change of that, that gives rise to an electric field, but it's a curl. There's a curl here, which means that that electric field is circular. It's a curl. There's another component of this, and there's a minus sign out here, and that's Lenz's law, and that's telling us something about which way those electric fields are going to be traveling. And then there's Ohm's law, J is equal to sigma. So Faraday's law, perhaps I've seen this too. We have a simple circuit. So we've got a coil, and then one end of that coil goes up to a voltmeter, and down through a little lamp bulb, and then back here, right? So it's just a little coil system, a little circuit. And then we take a dipole. It's traditional to have a north and south pole for magnets, with the north being positive, so that electric flux is going to enter out like this and come back in. So that's sort of the setup. And now we're going to start with the whole thing in a steady state. So the magnet is here, and the magnetic field lines, flux lines, kind of come like that. The important thing that we're going to be interested in is the magnetic flux that goes through. So that is just the integral over the area, so the area of the coil times the inner product of B with the normal component of that coil, integrated over that. So that's the magnetic flux. Magnetic flux itself doesn't do anything. I can have a really, really big field that's going through here and ain't nothing happening. But if I move that, if I change that magnetic flux, then in any particular circuit, I'm going to have a voltage that's set up. And the voltage that's induced is just equal to minus the time rate of change of this flux. In this particular case here, where the magnet is stationary, then that is going to be 0, so nothing's happening. However, the moment that I push that magnet in, now my magnetic flux is increasing, and so my voltage here is actually going to be less than 0, but there's, so there's current, it's going to be going in the other one direction, and there's current going through the light bulb lights up. Okay, we've got current in the circuit. If I do the other way around, pull the magnet back out, again, there's a time rate of change of magnetic flux, and in this case, the voltage is positive, so there's going to be a current that's going through, it's going to be in the opposite direction, but the light bulb is still on. Okay, so that's the basic elements. We have 2 apps that are generated to illustrate some fundamental aspects. There's one in the frequency domain, there's one in the time domain. And the way they're going to work is as follows. We've got, first of all, something to generate a primary magnetic field. So we've got an outer loop here, which has got a current I sub P, P for primary. So that can vary as a function of time. And then we've got an inner loop here, which is our target loop. And that has got a particular resistance and L, self-inductance. So that's going to be our primary app. And there's all kinds of parameters that you can change with. And I said there's both one for harmonic and one for transient. So let's just look at the transient. So here's our primary current. So we got a primary current in here. And our magnetic flux looks like this. If we look at the time variation of the flux, nothing changes here, nothing changes here, but right here is a discontinuity. So it's like an impulse. It's a delta function that's going on. So our time rate of change is a delta function. And over time, so that is going to generate a current instantly. The moment that happens, there's a current that's built up in that circuit. If I don't do anything else, that current is simply going to decay. And eventually it just decays away to zero with a time constant that depends upon this ratio of inductance over resistance. Okay? So, Sabina, is it? So if I do a time rate of change of flux on Sabina, you know, initially if she's got any conductivity at all, okay, there's going to be currents that are induced. And then if I don't do anything else, those currents just gradually subside. By the way, even if she is not conductive, I do a time rate of change of flux, there is still a big electric field in her. That electric field is going to be everywhere. But it has significance only if there happens to be a little bit of a conductor there, and then Ohm's law kicks in, and we're going to have a current. So what does the response function looks like? Well, here's it's E minus t upon tau. I can plot it in different ways. If I plot it on a log linear scale, so I take the logarithm of this, then that's just t upon tau. So I get these straight lines. So as a function of time, the response just decays in that linear manner, and the slope of that line depends upon tau. If I plot it in a linear plot, now you just see the exponential decay, and it looks like that. Okay, time domain, simple. That's all that's happening. What happens if our system is harmonic? If I have a harmonic current? Now, well, the main difference here is that in a harmonic signal, the primary current is always on. So if I look at this system here, the red is the primary. It's like this. And my current in here is the secondary current that's built up. So it's always on. So it doesn't decay down, it stays like that. And if you think about it, it doesn't have any choice but to be harmonic, and it doesn't have any choice to be harmonic at any frequency other than the initial primary frequency. That's the only thing that's happened. So somehow it has to adjust itself so that it's somehow at the same frequency. And then once something's at the same frequency, the only thing that can happen is that, okay, it's got an amplitude, and it also has a phase. So if you notice, here's the secondary field, secondary current, and you notice how it's phase shifted from the primary. There's a difference here of psi. So that's what happens. So the primary field is going like this, and the secondary current has got also that same frequency. Now I could take this green curve, and I could decompose it into two. I could decompose it into a part that is exactly the same as this. It's called the in phase. So it would have its peak here, and a negative here, and a peak here, right? So that's this part. And then I could also have another part that's completely out of phase with it. So it looks like this. Bottom line is I take this, I add that, I get the green. Okay. So the only thing I'm doing here is decomposing this signal here into something, well, into two. And they're very specific. One of them is in phase and the other is out of phase. If we take a look at an equation that represents that, that secondary current can be written as an amplitude and the cosine omega t minus some phase shift, which then you can take this, expand this cosine of angles, to get something like this. And you see that, okay, there's one part here that's changing as cosine omega t, and that's got this amplitude. There's another part that's changing timing over t, and that's it. Okay? We call this, and this is where probably the greatest confusion of electromagnetics comes when an EM person is talking to a geologist or even a seismologist or whatever, because you talk about this like, okay, that's the in-phase part, or that's the real part. Oh, it's just that amplitude. And here, there's even greater confusion because you say, oh, well, that's the out-of-phase part, that's the quadrature phase part, that's the imaginary part. All those terms mean exactly the same thing, and unfortunately for most of us who are so immersed in this, we often use them interchangeably, sometimes in the same sentence. But yeah, that's what you have to realize. I mean, this is just so straightforward and fundamental that we're just simply taking this curve here and we're representing it as the sum of this guy, and we're calling these the out of phase, the quadrature, the imaginary components.
And the phase shift depends on what?
So the phase shift, you're great. You always ask exactly the question that I'm going to respond to in the next sentence. So we're completely in tune here. Okay, so the phase lag is given by this expression here, pi upon 2 minus this guy, omega L upon R. And this quantity here is called the induction number. So that's our induction number. And the response here, that phase shift, doesn't depend upon these individual parameters. It only depends upon that combination.
So omega L and R are what?
So omega is angular frequency, so that's 2 pi f.
Yeah.
L is the self-inductance of your circuit model, of your target, and R is its resistance. So that's when it's plotted in a as an electric circuit. I'll show you in a minute how that compares with what happens when we work with a geologic.
So it does not depend on the size of your experiment? So the resistance, then the inductivity or induction. This is then
this is obvious.
Of the current,
it will in reality. This right now we're just kind of thinking about this 2-coil system. Just this guy here, right? So I've got this inner coil here, so which has got a resistance, but it's also got a self-inductance. If I change, the electromagnetic flux on any part of this wire, okay, it generates magnetic fields that are time varying. That affects the next little chunk of wire, and everything affects everything else. And in the end, everything gets lumped into one number, which kind of signifies what all of those internal interactions are, and that's the self-inductance.
Calculate this number, or it's more?
Yeah, you can calculate. You can calculate that for a loop. There's a nice expression for doing that. We're not going to be concerned about that at this point, because what we're going to do is we're going to go from this little circuit model, to then eventually a more distributed body. But this is a way of establishing what the connection really is. Okay, so we have an induction number, and if I then compute what the in phase and the out of phase are, so if I come back in here, so I've got this induction number here, and I've got it psi. So here's the psi right here. And now if I compute the in phase and the quadrature phase as a function of this induction number, then I get something that looks like this. So I get an in phase part that's the solid line, goes up like that. So at very low values of induction number, it's 0. At very high, it's 1. The quadrature phase at very low induction numbers, like this, and then it kind of comes up. That particular image is iconic because this tells you how the system is going to behave as you change the induction number. And for most cases, L and R are going to be fixed. You've got a fixed geometry there. And what you're going to be looking at is frequency along here, because higher frequency, the farther you are along here. So that's generally what we're thinking about. Okay, so that's our response function. We're going to see that a lot today, and it holds a lot of very meaningful information about what's going on. So in summary, what have we got? We've got a time domain, we have step off, frequency domain, we've got harmonic, nothing different. Time varying magnetic field generates currents, we generate magnetic fields. So the physics is the same, just a few details are different. Okay, so we've done a time varying field, and now we've got some current someplace, right? Right now it's still in that inner loop for our coil model, but we've got some currents. What do those currents do? Well, now we have Ampere's law. That current gives a magnetic field, but again, remember it's a curl, right? So if I have a current density, it's going to give me some kind of a. And now we have to measure this. So I've got a couple of options. I can actually measure B directly with a flux gate magnetometer, and that would be any one of 3 components. Or I could have a coil that's sitting up here. So a coil would measure a time rate of change of flux through there, and that would give a voltage. So I'd measure single voltage, and have three coils. I could measure 3 numbers. So now we've got to come back to coupling again. So in the example I was showing you, so we had a primary field that was like this. So here's our transmitter. And then I had a target loop that was sitting like this. And in this case, that target loop is perfectly coupled. Notice all the flux that's coming down from the transmitter is coming through my target loop. So that's going to generate the biggest voltages, biggest time change of flux. So that is perfectly coupled. This, however, is not. So there's no magnetic lines of flux that are cutting that particular coil. So that's called null coupling. So depending upon what the orientation is with respect to your transmitter, okay, you will get bigger signal or less signal coupling. There's going to be 2 couplings. One is if this is really a transmitter and that's your target. But the other is, we got currents in the target, so you can think of those as being a source, and then measuring with the receiver. So there's two times that coupling comes in. Okay, now you're ready to put all together. So here's our situation. We've got a transmitter, we've got a body, we've got a receiver. We're going to represent those by 3 loops. Transmitter is loop 1, target body is loop 2, receiver is loop 3. So we want to really define that response. And what we're really interested in is the ratio of the secondary field to the primary field. Okay. Well, we're kind of good to go here, right? Because we now really understand what's going on. So here's loop 1. So first of all, if we're looking at the secondary field, let's imagine how we get that. So it's the transmitter from here, and here's our target. So there's got to be a coupling coefficient here that tells us how that coupling is going. And that's going to just be given by this formula. That's just geometric. So that gives us M12. And then there's another, we've got to get the information from here to here, so that's another coupling. So that's an M23. So look at the top here, HS, M12, M23. And then, we've got the response of the target, right? Well, that's just that response function here. So that's what this guy is. So so our secondary field is the coupling target to transmitter to target, target to receiver, and then the response to the loop. The primary field is just, we just got to go from here to there, and then there's a self-conductor. Okay, so that now, I mean, that's it. We now have a fundamental formula. If you look in any textbook for electromagnetics, you'll see this formula. But what we see here is now a thorough understanding of exactly what's going on. There's parts of it that are simply just geometry, and there's parts of it that are doing about the physics of that induction in the body.
So M is measured in meters, or?
No, M is dimensionless. So we're integrating like a DL and a DL. So this is units of meters squared. It's just orientation. Okay, so now what are things going to look like? Okay, suppose, is there anybody here who's ever worked with something called an EM31? Anybody heard of it? Ah, you guys are great. Okay, so what use? Yeah, do you have friends who aren't responding? Okay, so what's an EM31 and where did you use it? Basically pointing the finger at you.
Well, I mean, it's basically two loops which are on the end of the rod, and you use it over the field you want to take a measurement on. One loop is the transmitter loop, the other one is the receiver loop. You're using it.
And where do you what applications do you use it?
Your students.
What?
To teach students.
To teach students. So does this curve look familiar?
Sorry, which one?
This guy here. That was a long time ago. That looks like a Ricker wavelet. Good job. Okay, so try and find this. The system that I'm using is an EM31. So it's got just like this. So there's transmitter, receiver, right? And then it's pulling things. We're just trying to kind of move things like this. So values that we have are positive and negative. When I've got a time-varying magnetic field, so I get flux that's going into this coil, that's going to give rise to currents that are going to try to oppose that. That's the minus sign in that Lenz's law. So that means that there's going to be currents that are going to flow like this, and those currents are going to give rise to magnetic fields that kind of come up like this. So I've got a secondary field that comes up like this, I've got a primary field that comes up like that, and those fields are the same sign, so I'm going to end up with a positive. As I come over, as my receiver comes over this direction here, okay, when the receiver kind of gets, if the receiver is over here, now the magnetic fields are like this, so I've got no flux that's coming through that receiver coil, so that means I'm going to have to get a 0. If the receiver coil gets up over here, now I've got magnetic fields that are going the opposite direction. So now my secondary field is going like this. So here's my secondary field. Primary field is going like this. So I'm at a negative. I get like this. And then as I move back over here, I get something that looks like that. So my characteristic curve of moving something like a two-loop system over an object is actually given by this thing here. So I talked about this zero crossing. What's this guy? There's two zero crossings. Anybody tell me what the second one is?
Transmitter over the target?
Right, the transmitter is over target. So there's zero, as long as there's zero coupling, I don't get a signal, right? I got zero coupling over here because I had a strong secondary field, but it's horizontal, and so there's nothing hitting the coil. But if I have a transmitter over here, it's vertical on the coil, so there's no current, and so they're going to get a zero. And then I come over here, they're both on the same. So I get this kind of a shape of current. So that is geometry. The shape of this guy is geometry. But then there's a red line and a black line, and they are the values of the in phase and quadrature phase. The black being the in phase, red quadrature. They overlie each other because we're at an induction number of 1. Okay. If I change that induction number to 0.5, now we see that the in phase is less than the quadrature. So you see that's what happens here. So the shape doesn't change. So the shape was depending upon geometry. The values, the relative values of the real and imaginary, do change, however. And if I go the other way, make alpha high induction number, I go like that. Okay? So that's what happens in the frequency domain. What about the time domain? In the time domain, any curves will look the same, right? So my curves look like this. And that's because that's just all geometry. But what I do notice is that for very early time, so let's take a time, black line, 1.1. So at very early times, I get the highest response. So it gives me this at time t1. And it gives me something less at times t2. So that's what I would expect if I had a time domain system going over that same object. If I was able to take that harmonic transmitter and just change it to a time domain system, and that's what I get. So what have we seen so far? We kind of get an idea about mutual couplings and response functions and data and time domain systems. So the circuit model seems to provide some representative results. So the question is that applicable to geologic targets? So let's just take a look at this. So here's what happens if you have a sphere in a background. So let's first of all we'll have our circuit model, transmitter. Here's a coil. Here's a receiver. Coil is 20 meters above the Earth. Coil separation 8 meters, and we get a response function, and it looks like this. What we'd like to do is to represent this in a numerical way, and we can do this with a full 3D EM code, but it uses cylindrical symmetry. And this is what Lindsay has been the primary author on, and a few other people have contributed. Basically, it does a system with cylindrical symmetry. So you can see that you could do that here if I had a transmitter that's sitting right up here, directly above. And now I look at the rotation symmetry. I could actually emulate this whole thing exactly, solve Maxwell's equations, and then evaluate what the response is. And you can see here's the response from the coil, and here's the response from the numeric. So you've got this nice quadrature part, you've got the real part. So this code is built on Simpay using Python. It's open source, so that is provided to to people here who want to use it. There's a couple of formative papers, one by Crocodile and then importantly Lindsay's one here, and it comes with with an app that you can go ahead and simulate cylindrically symmetric things. This actually turns out to be an extremely valuable code, not only for something like this, but it also handles magnetic permeability. These days, one of the big problems in the oil companies is that they're trying to make use of extended electrodes by using existing wells. So what you have there is a steel case or a steel casing well that's basically very conductive and very permeable, magnetically permeable. And so you want to simulate those responses. So with this, you can actually look to see, okay, where's all the currents, what are the fields, what are the fluxes, and get a real sense of what's going on. And I'll tell you, it's those fields can be quite complicated, especially as you start changing that ratio of permeability to conductivity. Anyway, that's available, and that's what everything is built on. So we're doing okay. We've got 2-coil apps, and we've kind of shown that they're a good place to build intuition, the 3-coil system. And now we're addressing things that we haven't yet talked about. And that is that we've got this transmitter here. We've got to get the energy from here down to the target. And we also have to get the energy from here back. So what's the big deal with propagating energy from a transmitter into a very target? The main thing was this geometric fall off of the transmitter is 1/r cubed. But what's the other issue?
The signal is strong enough to
Yeah, that's what we want. That's true. We ultimately want to have a signal strong enough, but what might impact on that? So we've already decided that. Pardon me?
shields. So you are flying, so you're transmitting it through the air, yeah?
Yeah. Well, I could be on the ground too. Doesn't matter. Anybody?
You mean the impact on the receiver side?
Well, we've talked about getting, what I'm trying to get at now is that the thing that we haven't talked about is getting energy from here down to the target and from the target back. And we're interested in getting enough signal. So certainly that 1/r cubed fall off in each of these from geometric data is important. But what else is important, if anything?
Yeah, because if the target is very conductive, you're gonna lose the magnetic electromagnetic energy. So you will receive the energy gonna be weak. At the same time, if your primary magnetic electromagnetic wave is very strong, so I guess on the data side you're gonna see a very small contrast between your primary signal and the secondary signal. Maybe
I think so. Anybody else got to speak? Yes.
Just to try, maybe the distance between the transmitter and the receiver, that spacing, does that matter?
Yeah, those things are all taken into account with the 1/r cubed fall off. Yeah, certainly your fields are going to decay, right, as you get farther away. Not run with it. Yes.
Yes, we have to account for the electromagnetic properties of the actual medium in which our fields are propagating, like the background conductivity of the rest.
Okay. So this medium up here might have some conductivity. If it's got some conductivity, then fields, there's going to be EM currents that are going to be induced here. Basically, there's going to be an energy loss potentially from the transmitter to the target, and another energy loss from the target back to here. So we need to kind of come to grips with that and understand that. So how do these fields and fluxes behave in a conductive medium? So back to Maxwell's equations. So here they are in first order. We can also write them in second order, where we have both this diffusion term and the wave propagation term. So here's the GPR. We're going to take Fourier transform of that and write this equation in this form here, which is basically a vector Helmholtz equation, where this quantity here is the wave number given by this quantity. Under the condition that this holds, omega epsilon upon sigma. So now you're talking like high conductivity, low frequency. If that thing is much less than 1, then we are in what we had talked about before, which is the quasi-static regime. And in that case, K can be written in this manner as a complex number, alpha minus I beta. So if we think about a plane wave, so a plane wave is a wave front, that's a plane, every point on here has got the same phase. If you want to think about it physically, you can think about a large current sheet up there. So big current sheet, and if the current is all going this way, then the magnetic field is going this way, and the whole thing is propagating down this way. If I look at that magnetic field, which will now be one-dimensional in depth, so here's our current sheet. Here's the magnetic field, the electric field, here's the wave propagation. It's got two terms. There's a phase term here, so that's a propagation. But it's also got this part here, which is an attenuation. So if I look at that, and if I plot how that electromagnetic wave decays as it goes into the ground, here's depth, and here is at the surface it starts with an amplitude of 1, and at some point it decays to 1 upon E, and that's called the skin depth. And skin depth is going to formula that looks like that. The higher the conductivity, the higher the frequency, the shallower the penetration is, or the shallower the skin depth is. So that's a really critical formula for electromagnetic. It's something called the skin depth. In time domain, if we wrote out the equations, we can get a solution. What we're looking at here is the amplitude of a wave as a function of time. So if I use Sabine again as an example. So suppose I've got a current here. I turned it off. So there's a time varying flux that's going in. Initially, she doesn't feel anything. There's nothing that happens until after a certain length of time. And then the magnetic field at her location starts to increase, and it will reach a peak at some particular time, and then it just decreases through. So the wave, rather than being like in seismic, like perhaps nothing would have happened, and nothing, and big pulse, and then nothing. Okay, that's the wave propagation. Here we're diffusive. Stuff starts to come in at a particular time, rises, and then falls. This is the basic reason why EM is never going to have the resolution capabilities that seismic does, right? So you can think about this as your time domain pulse coming in, and that is really broad compared to something just. Okay, so that's what happens as a function of time. If we took a snapshot after I had put this pulse off, if I took a snapshot at this magnetic field and looked to see what it was, what it was like, then there would be some point at which, some depth here at which it is a maximum value, and then it's decayed. Right. So That's what the field would look like as a function of depth. Okay. There's a formula for this peak here, which is given by this formula here, and written like this. So this peak is clearly going to increase as t increases, and it's also going to increase as sigma becomes smaller. Okay. This is called the diffusion distance. So we've got two things going. We've got skin depth and we've got diffusion distance. We have some apps for you. There's a plane wave app that takes you through this. There's both, there's two. There's a transient and then there's a harmonic that allows you to look at what the fields are. They could be real and imaginary, or because real and imaginary, you always put amplitude phase. And there's frequency, change this, do a whole bunch of things, and look at what those fields and currents look like.
Time delay before your signal starts to rise is distance dependent or depth dependent, or
Yeah, it's depth dependent. So it'll, yeah. So and nothing ever travels faster than the speed of light. So it's going to take a certain amount of time before you see anything, and then things are going to gradually diffuse through, and then they go down. It's just this little smidgen. Okay, so now let's come back to this background resistivity. So we've got energy that's here, goes down, comes back up, and it's attenuated. Yeah, so it's attenuated because of the frequency or the conductivity of the medium. So let's start to get some intuition about what's going on here. So let's first of all look at the effects of the background resistivity in the time domain. What we're going to do is going to vary a sphere, 2 centimeters, or 2 centimeters per meter. This is the surface of the Earth. Here's our transmitter sitting up here, 20 meters up. And now I'm going to look at, so I'm going to switch that system off, and I'm going to look at 10 to the minus 5 seconds. So 10 microseconds after turn off. And I'm going to look at the current densities. And this is what you see. So we've got currents here that are kind of illuminating the outside of the sphere. Okay, that's nice, showing that we're exciting it. A couple of questions. Why is it confined to the outside? Why don't we see something in here?
see only contrast. Inside it's the same resistivity, or
inside it's the same resistivity, but we're talking time varying fields generating currents. I mean, at some level, you might think that currents could
but
be
you're building your voltage only at contacts.
No. This is okay. So this is. So we did some stuff this morning on DC resistivity. We talked to charges, right? Gone. Okay, that's over there. Now we're doing EM. There are no charges in here whatsoever. There's only currents. There's no currents that are crossing this boundary. Those currents are confined to the sphere. You're just going around with that. My question is, why are they not inside? Yeah.
That's related to the skin depth of the anomaly itself. It's highly conductive, so it has a very shallow skin depth.
Good point. Anything else? Yeah, how would you, that is a good point. To see if, in fact, the energy is kind of confined to here. So remember, this is a 10 minus 5 seconds. To see if your hypothesis about the solution is really correct, how can you test that?
I would an anomaly of different connectivity.
So the thought process was that really we simply just can't get anything in here because skin depth is so small, right? So skin depth is it's kind of a frequency domain system. To think about things with respect to currents that might come in, you'd actually have to look at the full suite of times and then see, actually, do I get currents that are coming in here? And in fact, we'll do an example later that you show as a function of time, the currents actually build up and they kind of diffuse into here, and I actually do at the end have currents in here. At this particular point here, and you actually are like almost at the right point that I was trying to get at, there's currents that are defining just on the outside here, and that's because of this is a time domain, so it's diffusion distance. At this particular time, with that particular conductivity, the currents can only, or those fields can only get in a certain distance, and that's where they are. Okay? Now, what's going to happen if remember we just did this whole business of changing conductivity. What's going to happen to those currents if I increase the conductivity of this background?
We'll get a current in the background as well.
Get a current in the background. So I'm going to take this 10 minus 8, and I'm going to increase that to 10 minus 2. And I'm still there. Okay, so I've increased the background of that conductivity, but it hasn't made much difference at this point. But if I increase it more, now we get to here. So now this is now 10 to the minus 1 siems per meter. Now if I increase it more, this is what I get. So here you are. You got some currents in the background, and you got some currents on here. So things are starting to be shielded. You're not getting as much current on the sphere as you were before because stuff's happening up here. And if I increase it even more, so now this is 1 siem per meter, and I get this. So now I'm in a system where I've got a big conducting sphere here, but the energy is simply not getting in at that time. Okay, so we put all that together, and we look at the effective background resistivity for a time of 10 minus 5 seconds, and this is the progression that we see. So if it's completely resistive, no problem. As it starts to get conductive, then we get a little bit screened, and at some point we're just completely screened. So that was in time. Let's do frequency. And from what I've just been telling you, there's no difference between time and frequency. So let's do frequency. So here's the same scenario, but now I'm going to work at a frequency of 10 to the 4th hertz, so 10 kilohertz. And I look at the currents, and they look like this. And now if I increase the background, they still look like that. So again, that hasn't made much difference. Increase the background more. Now I get this partition up here. Increase it more, it looks like that. So at one frequency, if I change that background conductivity, I have the same scenario. Time, frequency, kind of look the same. Fundamental principle is that you can also get currents that are generated in some background. Okay, so what have we learned? Learned some stuff. Circuit model is a good proxy. We need to account for energy losses. I think we're ready to look at some field examples. So I've got a whole suite. We may not get through all of them, but they're all on the slides, and we can certainly talk about some tomorrow. DC resistivity, we've already looked at that. That was mineral exploration. Self-potentials, just flip through that. Denmark, this is an example. I don't know how appropriate this is for Switzerland, but this is a very nice project using time domain EM for hydrogeology purposes.
Actually, though, this is very significant because this is, with all the chance, this is quite an issue for finding nuclear waste.
Oh, okay, good. Oh, thank you. Good, so we'll definitely do this one. So that's a time domain system. And for frequency domain system, we've got an issue of contamination by of salts by irrigated farmland. So we've got salts that are coming down, and there's a floodplain down here that they're trying to monitor and perhaps restore. We've just been to Vienna, and we captured a case history there with respect to a landslide and the use of their system. It's a frequency domain system. So that's a time domain here and two frequency domain systems. We have another time domain system. This is actually pretty interesting. This is from Saudi Arabia, a guy named Danilo Colombo. And for there, they ran SkyTAM data, time domain EM system, over the area to get a better estimate of the near surface structure. And that actually then transformed to a better velocity model from which they could then get a better reflection seismic image. So those are the inductive sources, time and frequency. This afternoon, we'll do grounded sources. So I'm going to show you one from the Deccan Traps in India, kind of a larger scale. There's a couple of things, I don't know, maybe you're actually interested in this Barents Sea. You said that you were working there. It's this kind of source EM for hydrocarbons. Also, there's methane hydrates, which is becoming a big, becoming an important topic. Japan's probably going to start producing these guys. And we then go to the magnetotelluric side. Magnetotellurics is for larger scale things. So we've got a very nice case history for a geothermal system in Iceland. And there's also kind of a related topic in Sweden for landslides and quick plays. They don't use actually magnetotellurics, but they use radio stations that cover a nice spectrum. Well, of course, we have the famous rock glaciers from Switzerland. Maybe I should just get Hans-Rudi to talk through the slides there. Here's a really great, it's a cool example. I'm not sure how many people on the GPR side have recognized the potential use for GPR for self-driving vehicles. Anybody come across that? I'll tell you about that. That's really cool. And then in Denmark, there's a landfill study. So this uses IP, so it's GPR. This is IP, and then we're going to come back to Mount Heights and Mount. So that's kind of where we are. We've got other slides that are captured on the website, but if we can get through most of these, I think you'll have a good understanding of the applications, but we're also going to do all the fundamentals so you understand what each of these guys are. So the next step is we're going to do inductive sources. Oh, we have to introduce the PDF. things are growing as we go around, because it seems like each place we go to kind of capture another case history of it. So when we first started, we were doing these inductive sources, and it was a pretty big PowerPoint file. And then we kept dumping in more and more case histories, and now my computer won't even load up with that in. So we're going to switch from PowerPoint to a PDF. You can see there's 168 slides there, and a lot of them are high-res images, so it's kind of massive. Okay, motivation. Well, we've already seen that. Large areas, maybe groundwater issues, high resolution, shielding problem, trying to find minerals, rugged terrain, lots of reasons for doing inductive sources. So we're going to do a basic experiment. I'm going to talk about transmitters, receivers. Then we're going to do time domain system, and we'll do a case history, certainly of the groundwater, given what Hans-Rudi has just said, and then we'll do a frequency domain system. Always, when we're faced with practical problems, we got a ton of questions, right? Okay, what's the target? Is that the surface? Is it buried? Is it 1D, 2D, 3D? What do we use for transmitter? Yeah. What's the location? Is that the surface, in the air? What waveform? Frequency, time? What's the size? What's the size of the system? What's the footprint? That's an important part. Footprint is a really good thing. And then what about exciting the target? What's the conductivity of the target versus the host? The geometry, the coupling. Which fields to measure? What instrument do we use? It's just like a zillion questions, but you can't, there's nothing that's generic, right? You just, like, each time you're confronted with a problem, you have to kind of address all of these things. So let's start with the basic experiment here. So we've already kind of done that. We have a transmitter that produces a magnetic field. We excite the target. Time-varying magnetic field generates electric fields everywhere. And if you have conductors, you get currents. And then you got the receiver that measures the secondary component. Is that too big or something? Because I'm having to double click here. Yep, that worked. Thanks. Okay, so what do we got for a transmitter? Well, so we got large areas, got rugged terrain. We want to do airborne. Okay, so we could do airborne. Types of things look like this. That's a resolve system. That's a frequency domain system. That's a bird. And here's a time domain system. Scott can talk about those. If we have deep targets, we're going to need a large loop. And maybe, as we were talking just at coffee, a large loop might be useful for some of the projects here. But if you have a deep target, here's a large loop. So this guy here, and we've got a very nice case history with respect to him. It's kind of interesting. So here's a large target loop, or large loop on the surface. That's a couple of kilometers on the side. And you're trying to look at something that's actually a kilometer at depth. And actually, these are the lines at which the data have been acquired.
So you have one stationary large loop.
Yeah.
And you're then moving your receivers.
Yeah. Actually, this one's really cool, okay? Because these lines here that you see, these blue lines, that's actually an airborne craft that's going, and it's measuring the total magnetic field. So it's just a high quality total field magnetic device. But that actually gives us, it's like measuring one component of a time domain system as you're going through here. So these are all of the But the amazing for there was good, and actually there's another thing I'm quite proud of. Again, our group was like the first people to do a 3D inversion for this kind of data with this kind of a system for minerals application.
You must have an idea about your target depth and size of the object to have already the loop in the right place and the right size.
Correct. Yeah. So this is a place called Lalor. It's in Manitoba, Canada, and they've done initial discovery and they've done some drilling and they found stuff further up. So they kind of knew, okay, there's something happening here, and then and here's an interesting thing, right? So we've got something that's happening down here. You want to put a big magnetic field in there, and you want to couple, right? So does that mean you should be directly over the target? Because that would give you good coupling. Or do you want to be, like if I had the loop here, now I have a magnetic field, now I've got a good coupling with you. So there's some really interesting issues about, okay, where best to put the transmitter if you hypothesize that there's something there. So here you come back to forward modeling. You think, okay, maybe I've got some kind of a sheet in this way. If I'm put this guy up top, maybe I'm okay. You could also move this around. But a couple of kilometers of wire is, you don't want to drag it too much. So what's the issue? The issue is getting energy into the ground, exactly as you said. So it's the moment, which is the current times the area, and you could also wrap that coil wire around a couple of times, and so it's the number of turns. So that's the big issue, and that's why this guy is so large. And then remember, you've got your formula for the B. So the main thing here, as far as exciting the body, is that you got to remember your primary field's falling off is 1 over r cubed, and then you also have this attenuation that's coming through. You want to be as close to the target as possible, so that means that your transmitter should be as close. That's again why that ground loop was a good one. So that's the best. Helicopter is the next best, and fixed wing aircraft is the third. And you always need to be concerned about coupling. The receiver and the data, just the same as we were before, B or dB/dt. So the receiver in the time domain, okay, is always going to measure the kind of the secondary current. So imagine, so we've got something, time domain, shut it off, builds up currents. Now I'm just going to measure the fields from the decay of those. So the receiver could be up on this platform or in the air, as it is here, or on ground. A frequency domain is different. And here's the complication, is that the primary field is always on. And the primary field is actually large compared to the secondary, by often a couple orders of magnitude. So that's a challenge. So if you're going to use a frequency domain system, you somehow got to get rid of this primary field. So you could compute and subtract. Okay, so if you know the exact coil transmitter. For frequency domain, the thing that is usually done is that they'll have what's called a bucking coil. So the primary field coming in here, okay, is going to generate a voltage, that's the primary field. But if you established another coil here that had the same flux but in the opposite direction, then you cancel out the primary. That is what's usually attempted to do. So you hear the term bucking coil. All that's trying to do is to get rid of the primary response here, so that then everything else that you measure is coming from the ground. The configuration of birds is usually like this. So you have independent transmitter coil and receiver coil. So they kind of go in pairs. So it's like this red and that red. It's a and that's a 400 hertz coil. And then this guy here, the yellow and the yellow, that's 140 kilohertz coil. So you got 5 different horizontal coplanar. So the loops are horizontal and they're on the same plane. So it's kind of horizontal coplanar coils. You could also have vertical coaxial coils. It's the same axis. So that's those are the 2 types that you generally encounter. And here was that EM31, looked like that, had a single transmitter, single receiver. That operates at around 10 kilohertz. So you only see stuff that's really pretty shallow. Okay, so that kind of gives you a bit of background there, but now what about the data? So where do you collect them? How many? How accurate? Depth of investigation? Footprint? So these are all questions of survey design. And we're going to kind of try to step through a little bit of that, first of all, in the time domain. So let's suppose that we've got a system that looks like this. So we've got a current, and you shut it off, and you've got something like this. So if we have a B-field receiver, it's going to look like this. So the magnetic field is just going to come down. If you've got a coil, then there's going to be an impulse, and then the decay. I think the most informative way of trying to understand any of these things is look at the currents. What's the footprint of the system? Look at the currents. So we're going to see a lot of pictures like this. They're going to be cross sections through the Earth. So here's our vertical magnetic dipole. This is air, and here's the currents in the Earth. And we're just going to look at that kind of system under various scenarios. So here's the system. Here's the coil, transmitter, and then you see the little red dot, that's our receiver. And half space, 100 ohm meters, we're 20 meters above, air is infinitely resistive. And we're going to look at the currents, see where they are, how those currents depend upon the conductivity, and what the resultant magnetic fields look like. So we're going to have 2 sections of drawings, or of plots. So one is a vertical cross section, and the other is a plan view map. So let's look at current density to start with. So we've got a vertical magnetic dipole. So the current in the loop is going like this, right? Let's go like that. So in the ground, currents are going to be following the same direction. So the currents in the ground are going to be circular. So they're going to look like that. So we look at a plan view map. Currents of the ground are going to be 0. There's actually not going to be any current directly beneath the loop. And the currents at any particular time are going to be kind of away. Whoopsie. Be away. So it looks like that. If we look in cross-section, then we've got a map that looks like that. So the currents are going in here and out here. So they're going to. If we looked at the magnetic flux, if you look at this, you can say, oh, where's the magnetic field? Wow, the strongest magnetic field is probably going to be right in here, right? So each of these are all like little loop filaments of current going into and out of the board. So that means, each of them is going to be like a magnetic dipole. So you're going to have the strongest magnetic field here. And yeah, your intuition would have been correct. So these are the lines of magnetic field, shows direction, but the strength is in color-coded contours. And we're sitting up here, so we can measure the magnetic fields that are due to all of those currents. Currents flow in here, we generate the magnetic fields. We're sitting up here. What we're going to do now is we're going to step through time. So we've shut this current off. We're at, this is 0.002 milliseconds, so it's 2 microseconds. And remember that formula for the diffusion distance like this? That comes out to about 18 meters. And if we look at the currents in the ground, they look something like this. So this is 50 meters, so everything's there. Now, if we look at time later, diffusion distance 38 meters, kind of looks like that. Time later, 75 meters. So here's what happened. The moment I turned those currents off, or turned the current transmitter off, I then got currents that are flowing circularly in the ground. And as time progresses, those currents kind of go down and out and gradually decay. That's a diffusion. Misak Nabigian, many years ago, 1979, wrote a seminal paper about smoke rings, which was a way of trying to understand kind of conceptually what's going on with the currents. And he basically showed that the centroid of the currents kind of goes down and out. And that is exactly what we're seeing here. So here's a early time, later, and later. And it's kind of following those particular angles that were set up. Okay, yeah.
What's the angle? Is that exactly 30 or is it just approximate? So is there a reason for?
If he evaluates where this center was, then kind of comes out to be about 30. From our perspective, that's totally unimportant, right?
Okay.
Yeah, it's just these are the currents, right? They're diffused. There's currents, there's currents at the surface, right? So this is kind of something to help guide. This is an important thing, right? So I have a transmitter, I turn the current off. Those currents are initially in the earth, and then they go down and out. And also, I didn't talk very much about it, but we got yellow, we have the same color scale, but you have to actually look at the amplitude here. So this is 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. So the colors look the same, but we're really losing on amplitude. So that's the important points. Currents flow in the same direction as the transmitter. They flow downward and outward. Each transmitter has a footprint. Maximum resolution, if you're going to try to think about times and resolutions, what would be the connection, if you can think about any, between your ability to resolve structure in the earth and which time channels you're really interested in? Anybody? You guys. What would you say?
Early time from similar, late time.
Yeah, so your best resolution is going to be at your earliest time, right? Because that's, all the currents are confined to being up here. So you're not influenced by anything else. So those are your early times, give you your highest resolution. The latest times actually tell you more about, okay, how deep am I really seeing? Your resolution is definitely going to decrease as you go down. But there is a question like, oh, how deep can I see? And you can't see any deeper than the deepest currents. So that's kind of the two end members of what you've got.
What is the typical depth where you still get a decent signal from?
It just depends entirely on your transmitter, on your background conductivity.
Yes, but technically doable. So we say in seismic, you can get decent high resolution pictures, say from 3 to 5 kilometers.
Well, no, it's a bit more dependent upon the nature of the transmitter. For instance, if I had that large loop transmitter, I'm seeing down 1 kilometer. Okay, if I actually had a magnetotelluric signal, I can see down 100 kilometers. If I've got something that's really small. If I've got a little GPR antenna, for instance, I'm only going to see down centimeters. So
but down the 100 kilometers, there's no actual target object. This is like crustal structures or something.
Which is the target for some people, right? They want to understand what's the crust like, what's the mantle. And sometimes there's hot spots that are coming in. So, looking at volcanoes or anything, and looking down 15, 20 kilometers, not totally out of the question. So there is no answer to that question. But if you have something, let's suppose you have a geology and you've got something at a particular depth, then you can say, okay, what would I need to do to actually see that? How do I put energy in? And the fundamental things I'm talking about is like, okay, we need moment. So, maybe I need a big loop, right? Or whatever. So now we're good. Now let's come to something that's a little bit more, well, everything is interesting, but it's even more interesting. It's a bit more complicated. So we're going to have a 4-layer Earth. So we've got basically that homogeneous 100-meter Earth, but there's going to be an intermediate layer of 20 meters thick, and it's going to, we can make it different resistivities. We could make it really resistive, or we could make it high resistivity, low resistivity. So here's what happens. It's a uniform Earth. The currents look like that. Now what I'm going to do is put in a resistive layer in here. Put 1,000 ohm meter. Then my question to you is like, okay, what do you think is going to happen? Okay. I put 1,000 little layer in here, 20 meters deep, 20 meters thick. What's going to happen to the currents? And why?
Focus more on the top part.
Focus more on the top part?
Yes.
Yeah, could be. That's one option. Any other options?
Well, nothing will happen in the place where we have the high resistivity. I mean, no induced currents, but then below that, like we have also below the air layer, we have below the.
So this is what happens if I put a resistive layer in here. I get currents in here, but interestingly enough, I actually get more currents at depth. So I put a resistor in here instead of kind of channeling things and trying to keep it above the resistor like it did in DC resistivity. It does exactly the opposite. It's transparent to that resistor, and I can see even deeper into the subsurface. All right, so how interesting is that? Okay, now what happens if I make it conductive? And at this point, you guys know all these answers. What happens if I make it conductive? Am I still going to see down here? It's going to help, hinder? Anybody? Go for it.
I guess the role focusing on that.
We will still be.
Yeah. So if I put a conductive layer in here, this is the guy where the most currents are. So I'm preferentially seeing this conductor and not getting low here. If I do even more, then really all my currents are just in that conductor. And they're not even getting through that conductor, as you would expect, because we can't get rid of the fundamentals, right? The fundamentals are that there's only a certain propagation or diffusion distance that happens at a particular time for skin depth.
Just one comment maybe.
Yeah.
I mean, this actually here you have different color scales on the top and the bottom. So you would actually still get current in the top.
That is true. That is true.
Before. It's just not visible in that color.
That's true. Yep. Yeah. So these color scales are changing. I mean, we are still going to get some currents in here. It's just that from the point of view of where the currents are really being concentrated, they're concentrated on that conductor. So we're starting to see there's some really important things here, that inductive sources see conductors and they're invisible to resistors. If we looked at the magnetic fields from each of these, remember here's our dot up here, here's a receiver. So we see the magnetic fields are changing a lot, and we're going to see some response. Perhaps the best way of seeing this is something called a sounding curve. So in time domain, this is the signal that you get as a function of time. So if we just have a uniform half space, then here's our sounding curve. If we put in a resistor, so the dashed line is like the layered earth with the resistor, right? There's diddly squat difference, right? So if we're flying over with an airborne system, we're just not going to see very much. On the other hand, if there's a conductor down here, look to see how much different there is. There's a huge difference. And if that's at 10 ohms. So remember we're at 100 ohms, so that's only a factor of 10. And if we make it 1 ohm, it's just way out. So an inductive source system is going to be really, really good at seeing conductive units. If we look at a sphere that's buried, so now we're going to fly a system over a buried sphere. We're going to look at, so each of these dots is going to have a sounding associated with it. And then across the center of this, we're going to have a profile that's going to be plotted in here. So what we're seeing at this point is that on plan view, virtually all the data are the same. And on profile, they're all the same, and we're at like 10⁻⁵. A little bit later, you start to see the effects of that sphere, and on profile, it's kind of, so the overall amplitude is decreased, but we're starting to see something. And the sweet spot is coming in here at 0.35 or 0.3 milliseconds, where we see the sphere very, very nicely, and also see it on profile. And then later, things start to decay, and then gradually decay out. If I kind of summarize all of that, as a function of time, my plan view maps look like this, so there's a bit of a sweet spot. My profile maps initially start off nothing, and then I see the sphere, sometime later I see the sphere, and then everything decays. Okay?
What kind of equipment is able to record or distinguish 0.025?
No problem.
Yeah.
No problem. We'll show you some. So here's a system. Time domain system. There's two of them we're going to look at. One is the SkyTem system. So in the SkyTem system, here's your helicopter. Here's your loop. There's your transmitter loop. Here's your receiver. And it has to put in a waveform. So it puts in a waveform that looks like this. It starts 0, goes up, and ramps it off, and then stays 0. The earliest time that you can look at here is about 47 microseconds. That earliest time is really related to how much current you're trying to put into a loop. Because if you have current going into the loop and you try to shut it off, you can't turn it off instantly. There's a lot of self-inductances that's going on in that loop, and you simply cannot turn it off quick enough. But you can get something at 47 milliseconds or microseconds. You can turn it off faster if there's a lower current that's in here, and so they have a high moment and a low moment system. And the low moment system has a current waveform that looks like that. They turn it off faster, and they can actually get it back to 12 microseconds. I believe that the next generation that they're working on is trying to get back to more like 5 microseconds. There are ground-based systems that can, they're smaller, they don't need to have so much current, that can get sub-microsecond. The VTEM looks somewhat similar, yeah, kind of in a way. The waveform is more like a half sign, kind of goes up, and then it's like that. But most of these time domain systems are, pretty much the same. They've got some kind of a waveform, truncate to 0, measure in the off time, and yeah, the main thing is like you're just going to measure a whole bunch of time channels. Those are generally logarithmically spaced, and you're going to then work with those. Yeah, so the VTEM system has got an outer transmitter loop, like this, and then an inner receiver cloud. So let's do one quick case history. I'm going to do this case history for the Danish group, Kasten. So I like this case history for a couple of reasons. One is that it just showcases what you can do with time domain EM. The other is that it also shows where geophysics comes in the context of a larger problem. And the problem here is an area in Sweden, Denmark, sorry, where they were really concerned about where the where the groundwater is and how things are connected. Basically, you've got a background here. These are a lot of Paleogene clays, and then scoured out of that, you've got these paleo channels that are consisting of sands and gravels and a few interbedded clays and tills. But you're trying to find out these guys here. So these are going to hold the water. And then the question for the groundwater hydrologist was like, okay, suppose I put a pump here. Right? I start pulling water out. I pull water out here. Like, where's it coming from? Like, coming from over there? Is it over there? Like, where am I drawing the water from? The other associated question is, okay, if I put a well here and a well here, I'm pumping both of those out. Are those guys talking to each other? Am I sampling the same water supply, different? I mean, just what is going on underneath the ground? This is very important. I want to know it. So let's look at the physical properties. In this case, the main issue, at least as far as we're concerned on this first pass, is that the infill here are like coarse gravel, sands, that bears the water. And those are pretty resistive. They're generally at least greater than 40 ohm meters. Underneath here, this kind of blue area here, those are basically clays. They're conductive, maybe 1 to 40 ohm meters. And the other units within here, kind of betwixt and between. But that's essentially what we're essentially looking for. Is the top of a high conducting layer. So we're going to do a survey, a SkyTEM survey. We've got high moment, low moment system. Here's the transmitter. Here's the receiver. The low moment is, because it has a faster turnoff, is used to image the near surface structures. The high moment, you're seeing detail. The data, there's 300 odd line kilometers of data, 100 meter spacing. A lot of noise, maybe similar to Switzerland. So they had to throw away some of the data, but they still had a lot that was left. And then they're going to invert it. Now there's a whole bunch of ways of inverting these kinds of data. I think we're at the stage these days where, especially with multiple meshes and octrees and lots of computer core that we can actually invert like the full 3D data set, all the sources and receivers. The other way, and this is actually popular too, and it works, I think, very good, at least as a first pass, is that each sounding location, just do a 1D inversion. And you want over here, you want over here. So yeah, and then you just do all these 1D inversions, you connect them. But within the context of doing those 1D inversions, you kind of take account of what's happening on your neighbors. So you kind of put in lateral, it's called laterally constrained inversion. But that's a word that you'll popular here, or sometimes they'll call it quasi 3D. So generally what they're doing there is just stitching together a whole bunch of 1D inversions, but preventing the inversions from, well, actually making the inversions talk a little bit to each other, but not really solving the full 3D problem. But for a lot of cases, especially if you're working near surface, that's fine, certainly as the first pass. So what are we seeing? So that's what they did, 25 layers, and then now we're going to slice it at 5 meters above sea level. And here's the resistivity. So there's, the reds are high resistivities, and the blues are low. So these are conductive regions. And here's our incised valleys. So that's what's happening laterally on a plane. If you then look to see and interrogate this result and look to see, okay, what's the depth or what's the elevation of the top of that conductive clay, you see that there's these incised valleys. So now they're blue. So that these are really deep elevations. Those are like negative hundreds. And it's that side. So these guys here, the blues, kind of delineate those conductive, or well, they indicate those buried channels. So we got sort of 20 of the buried cross-cutting valley. So that was the output of that. And then the next set was to go back, take the 3D resistivity model that was generated, as well as combine that with some borehole information to actually generate a geologic model, hydrogeologic model that could be used with ModFlow. Okay, so now you take the resistivities, okay, and then kind of calibrate. Well, first of all, you find the depths, okay. And then within these incised channels, you've got a couple of wells, and you kind of do a proxy of those wells with the recovered resistivity, and then you subsequently do those recovered resistivities to try to decide, okay, what sort of layerings or units do I have elsewhere? Okay, so that now gives you a 3D geologic model to which you can assign hydraulic conductivities. And now you can put that into ModFlow, and you can quantitatively see, okay, I'm going to extract water from here, and I'm going to extract water from here. Where's it coming from? Well, it's not coming over here. It's sort of more coming up from up this channel. And similarly here, it's coming from here. And yeah, maybe there's even some, a little bit of talking back and forth. So I don't really know all the details, and I don't think they're really important at this point for that, but that's the process. I think that's a great process. That's really where a lot of certainly electromagnetic geophysics plays. It's part of a role in solving a much larger problem, and in this case, it led to them being able to develop that hydrogeologic model. Okay.
Just a quick question.
Yeah.
How long does it take to collect the data on this server, for example, approximately?
Oh, I don't know, but probably not more than a day or 2 days. Goes fast.
Yeah, because you can drill off the ball, but they cost a lot. So.
Yeah, no kidding.
Yeah.
Okay. Well, I think that's a good place to to stop for lunch. What do we? Is there a place around here for lunch? And so let's meet back at 1 o'clock, and we'll continue on. Good.
So you can actually use all the computers in here, we will not lock the door.
Okay. That sounds good.